Hello, everybody, and welcome to the second day of the Improving Scientific Software Conference, brought to you by the UCAR's Software Engineering Assembly. First of all, I want to thank our sponsor, Fluid Numerics, which contributed to you being able to attend this conference for free. So Fluid Numerics is a small business based in Boulder that participates in academic research and in supporting research-oriented organizations as they transition to cloud platforms and novel computer hardware. So a little bit of logistics now. Given the number of attendees, please only use Slido, which will be posted into the chat in a moment, for asking questions. Do not use the chat for questions, because otherwise we have too many things to watch, and the chat scrolls fast and it's hard to manage. And for in-voice discussion, given again the number of attendees, it's better if we can use networking sessions later today, where hopefully the speakers will attend. And also note that this conference has a code of conduct which is available on this website, which also will be posted on the chat. And so with that, let me announce the first talk of today, which is by Mark Coletti and Ada Sedova from Oak Ridge National Lab. And that's toward designing effective exascale scientific computing workflows, experience, and best practice. So with that, Mark, take it away.
Can you see my presentation?
Mark, you'll need to swap displays.
Yeah, we see the presenter's view. You might want to use the other one, so we just see the larger slide.
Boom, how about now?
Perfect.
Excellent. Hi, my name is Mark Coletti. I'm a staff computer scientist at the Oak Ridge National Laboratory. So I'm here with my colleague Ada Sedova to talk about toward designing effective exascale scientific computing workflows, experiences, and best practices. So Ada, if you can introduce yourself.
Hi, I'm Ada, and I'm a research scientist at ORNO, and I've been working on HPC workflows for some science use cases. So I'm going to tell you briefly some background and motivation for what we're working on. So what kind of workflows are we talking about? There are many different types of computational workflows. What we're talking about is massively parallel data flow execution model type workflows. Tasks may be heterogeneous, task scaling and asynchronous tasks are possible. And you generally need a workflow management software to try to make these run at large scale. There are many different solutions for these types of software: Fireworks, Pegasus, Radical Pilot, Parcel. Not all of these can scale to very large workloads. And so on leadership computing facilities like Summit, we have some challenges to work through. And generally what you have is a master scheduler that needs to regularly connect to each worker to check progress. And this leads to a lot of connections. Next. So here's an example of a workflow management software architecture. You can see there's just a lot of moving parts, a lot of connections to the UIDs of the workers, and a scheduler, a heartbeat. Next. And so on HPC systems, this is kind of new. HPC systems have been traditionally used to deploy specialized scientific computing programs with MPI, one big job running on the whole machine. And so now with the explosion of AI, there's a need and a desire to bring AI and HPC together. And so now we have a shift in the type of workflows happening on these HPC systems to try to accommodate some of these AI tests. And you have this new workflow type of paradigm happening. So you're bringing in not only HPC simulation, but distributed training, hyperparameter tuning, and data-intensive high-throughput calculations. Next. And so we've got efforts in material science, drug discovery, computational biology, and so many other things that are wanting to try to take on this paradigm and do some really new, interesting things. Next. So the convergence of HPC and AI is still a work in progress. Like I said, they're very different programming models. HPC, like I said, traditionally flop-heavy codes, synchronous, MPI. With data and ML, you've got Python packages, containers, servers. So this is kind of a hard thing to bring together, and we're still trying to figure this out. Next. So the Summit supercomputer is a 200 petaflop system that's at the Oak Ridge Leadership Computing Facility, OLCF. We've got 6 NVIDIA V100 GPUs per node, and we've got Power 9 CPUs with 42 cores, and it's all mounted on a GPFS parallel file system. Next. So how can we bring this together, HPC and AI? What kind of tasks? We've got a number of different things we're going to talk to you about that we're working on here. Next. So computational biology, there's an explosion in the number of genomes that are being sequenced. And so now you have a huge number of proteins that have unknown function. So we're trying to figure out what these unknown proteins do using HPC and protein structure prediction on the Summit supercomputer. Next. In materials science, there's a lot of data that's been collected about materials. There's traditional HPC simulations that have been done on materials, and trying to bring those together to design fancy new materials is a really hot new topic. Next.
So another workflow that we're working on at ORNL involves taking training data and passing it to an evolutionary algorithm running on the Summit that actually will train a convolutional neural network, but also do a hyperparameter optimization and neural architecture search. And the result of these runs on Summit will be a model that hopefully performs ideally for the problem that we're trying to solve. But next, we pass it off to an adversarial evolutionary algorithm called Gremlin, which tries to break the model, tries to find the weaknesses. So it will take this information of where the model performs poorly and update the training data with more examples of those particular scenarios. And then Mendel will resume training with that updated training data, and the cycle resumes. Where the complexity comes in is that we would like Mendel and Gremlin to run at the same time on Summit, but we know that they're not going to use the same number of nodes. But that doesn't really help us. So it would be nice if the system could kind of figure that out on its own. So one of the things we're looking at are different workflow paradigms that will actually support that on Summit. And
a final thing that's been happening at the lab at ORNL is trying to bring together experiment and instrumentation and AI. So there's some examples are running electron microscopes autonomously and using AI to do the image processing steps. This is a big project at ORNL. And then also bringing the spallation neutron source with its many different instruments for neutron scattering together with HPC and AI. So previously, we've done some work trying to scale these workflows on HPC systems like Summit. The Titan supercomputer was the one before Summit. We were running molecular dynamics workflows in large replicas, doing this advanced sampling in ensembles. And so we did manage to get the radical pilot workflow manager to scale on Summit. Unfortunately, it did not work on, on Titan, and unfortunately, it did not work on Summit. There were some issues trying to get it to scale on Summit just because the vendor was different, the architecture was different. Another thing that we worked on is creating these small scale testing of large workflows with in-house skeleton programs that showed on Summit that you can make about 16,000 or more connections to workers relatively easily. But these were kind of test workloads. And then we also ran at production scale drug discovery, massive full scale runs on Summit for drug discovery using the Fireworks workflow manager. Both of these methods, Radical Pilot, our test system also, and the Fireworks use a MongoDB, the Mongo database manager, as a queue manager. And that can be a little bulky. And as you can see on the right, the Fireworks took longer than an in-house version that was just kind of bare bones and coded up with a Redis in-memory database. Okay, so let's talk about an alternative approach that was a little easier to deal with and a little bit more robust. And this approach involves using something called DASC, which is basically a Python package that allows you to distribute computation. We found that DASC scales from running on your laptop all the way up to Summit. And you can basically run things at scale on Summit without too much difficulty. So I'm an evolutionary algorithm guy. And so I spent the last few years taking evolutionary algorithms and running them on scale using DASC. And so now we're going to get into brass tacks, right? We're going to actually share essentially some recipes or some how-tos that hopefully will be relevant and helpful to some of the listeners. So on the left is something called an asynchronous steady state evolutionary algorithm workflow. And this is basically the recommended way to run an evolutionary algorithm on an HPC platform. And why is that? So for those of you who are familiar with evolutionary algorithms, say a genetic algorithm, you have a population of individuals that is being updated by selecting parents that create offspring that you do use to update the population with. And over time, the population converge on an ideal solution. And it does so basically by stepping generation by generation. But if you stop and think about it, when you're evaluating individuals in the current generation,
you cannot proceed to the next generation until all of the individuals are evaluated. And it may be the case that some individuals finish their evaluation well earlier than their counterparts, which means that the corresponding HPC resource is going to sit idle until the next generation, which you don't want, especially on a big machine like Summit. You want to make the most efficient use of the resources allocated to your job. So what you want to do is this asynchronous steady state evolutionary algorithm. And as the name suggests, you are asynchronously updating the population. You're not waiting from generation to generation. So this diagram shows an example where you're done evaluating an individual, and then you play sort of the version of the reality show survivor. The population is that box in the lower left. So you select an individual from that population and compare it with the new guy that's firstly evaluated, and then the better one gets to stay on the island, or stay in the population in this case. Well, now you have a freed up resource that's not doing anything. We can't have that. So we select randomly an individual in the population. They're the parent, you clone them, and you mutate them and maybe employ some crossover. Now you have an entirely new individual that needs to be evaluated, and you assign it that freed up resource, recently freed up resource, and now it's humming along again. And you just keep doing that for the life cycle of the run, and it's a lot more efficient than the by generation approach. So with that said, here comes Ada with a problem that she had that she wanted to run on Summit. There's something called AlphaFold 2 that allows you to do a protein structure prediction. And the notion was that we could scale this to run on Summit. So I said, aha, I could take my existing EA code using Dask and repurpose it for your task. And so on the right-hand side is the result of that. So we have a flat file that has all the proteins. We just slurp all those in, and we just blast them all to Dask. And it has an internal queue and a scheduler, but basically of all the proteins that need to be processed. It fans all the first batch of proteins out to all the GPUs. AlphaFold is crunching away. Ding, one of the nodes is done. We pop off the next protein, assign it to that node, fire up AlphaFold 2, and now it's cranking away again. And we just keep doing that until the queue is empty. And because I had everything already set up with the EA, it took me about a day and a half to get that up and running, prototype. I won't tell you how long it took me, blood, sweat, and tears to get the EA asynchronous stuff working, but I was able basically to leverage that prior experience to help out Ada and her crew. So again, it didn't take long to get AlphaFold 2 working using the a modified version of the existing evolutionary algorithm framework. So how the Dask API was used to create a portable resolution is that Dask was appealing because, as you'll see shortly, it's pretty easy to stand up a prototype. It doesn't use MPI. I won't go into details, but just say that using MPI on Summit was problematic, so avoiding MPI was a big win. Dask, of course, provides a lot of documentation. But those of you that are the software developers know a problem with a lot of software documentation is auto-generated, usually from the source code. So it tells you the what, it doesn't tell you the how, and Dask suffers a little bit of that. But I'm here to kind of rescue you because I'm going to give you some recipes on how to use Dask. So remember in the previous diagram, these two things, I'm going to show you basically in Dask how to implement those. We're going to start with the simplest one, say the AlphaFold problem. So on the top there, on the top right, processing a static list of items, in this case, a static list of proteins. You just read them in maybe from a flat file, and you have a function called process item, which basically invokes subprocess, runs AlphaFold for that particular protein, right? And map, you just call client.map, which is a Dask function against a list of those proteins, and you get back something called a set of futures. And step 3, you have a for loop that uses this special Dask supplied iterator called as completed, which, as the name suggests, is as the tasks are completed, you get finished task is assigned to that as that recently completed task. You can pull out the result, maybe print it or do something else with it. And you just basically have that for loop to kind of tell you the progress that you're making as you're going through all those proteins. And that's it. Very, very straightforward. The evolutionary algorithm is a little bit more complicated because it's not a static list of items, it's a dynamic set. In other words, we're adding offspring, we're adding new tasks while it's running. So how do we do that? So just like with the protein stuff, we create an initial population or initial list of items to process. We call client map as before. Evaluate individual is a function that evaluates an individual, and we give it that initial population. We get the futures, and we pass it to the iterator, but as completed. But notice that we do this before the for loop, and you'll see in a second why I do that. So we follow in the for loop as before, So as each individual is evaluated, we get step 4A, we have the individual, we have the result. We might be able to print out something about the individual that was just evaluated. We update the population as I described before. Now you generate a new individual, also as I described before. And now you just want to evaluate that one individual. So you use client.submit, not map, because you only want to do a single evaluation. Are you passing that evaluate individual function, and a new individual, you get a future back. And now you see why I declared the iterator outside the loop, because it has a function called add, where I add that future that we just got from submit, because we also want to be tracked when that new task is completed. So there you go, 2 recipes on how to do something like that. Okay, now I'll talk about another little war story. And this actually happened to us last month when we were working on a paper to submit for the Congress for Evolutionary Computation. So I showed you examples using functions, essentially standalone functions, but it may very well be that you're using a Python framework that requires you to use a function that is part of a class instead of a standalone function, which Dask could do, no problem. But there are some caveats, some gotchas that you have to be aware of. Do not assume, for one thing, that class-based encapsulation works. With object-oriented programming, the notion of encapsulation is the data and the functions that operate on that data are all in a nice little happy bubble. Well, Dask kind of pierces that bubble a little bit, and I'll show you here in a second how that happens. So the class object data will not be local to the worker invocation of that member function, and therefore the data must be copied over TCP after doing pickling and then unpickling at the other end, which can be problematic if you have a lot of data that has to be sent over, which of course can potentially create a performance bottleneck. So this is a sort of modified version of the code that we used last month for the that paper that I mentioned. And you'll see that this is a class that inherits from something called LeapEC problem scalar problem. LeapEC is part of the library for evolutionary algorithms of Python. Is a Python library for evolutionary algorithms that I actually developed with some colleagues. And you have to, if you're going to be using Leap, define a subclass of problem to basically determine how your individuals are evaluated. So you see that this class has a member function, evaluate, and when you're using Leap, Leap will call Dask and give it this evaluate function, right? So here's a problem. The problem we worked on last month was where we're taking a Q-learner, but it could use any other kind of model. And we thought we were being clever. Oh, we say, we'll just create the problem and just in the constructor, we'll just create the model there. That way we're only loading it once. So that when you're doing the evaluate, hey, we'll just pull in the local model, self-dot model to do the predict and to get the fitness and return to fitness. And we're done. No, you're not. Because here's the trick. Dask will first of all complain that you're sending a lot of data. And that's your first hint that you're doing something wrong. That red dashed line there, you can think of as sort of a line of demarcation that everything above that line is local to the client and everything below the line is local to the worker, which means that when the worker runs the evaluate function of the Dask worker, it's got to pull that model over the wire. It's going to have to pickle it, transmit it, and then unpickle it. And now you have access to that model. And that can be expensive because you might imagine a lot of models, machine learning models can be quite big. So what do we do to fix that? So here's the approach that I recommend using. So another recipe that I'm going to be sharing with you. You can write a little function called setup worker. And what it does is invokes a function called get worker, because the idea is that Dask is going to run this in all the workers. And get worker basically gives you a handle on the worker, the current worker. And you just set up the model there and you assign it to an attribute that's local to the worker, right? And how you send that out to all the workers, you run something called client.run. And it will run that function on all the workers. And you can see that you can also pass in keyword arguments, in this case, the model path. And there's an important argument you need to set with client.run called wait. You need to set that to true because you don't want to proceed and go on to doing whatever important computation you want until all the workers have a model. So you need to say wait equals true. And on the right, you'll see what the impact is on that evaluate. It's part of that class. I just deleted the rest of the class for the sake of brevity. You can see that's a lot simpler now. It basically says, just get the worker and then run the model. And the model is local at this point is local to the worker. So there's no need to transmit the model. Okay. Sorry, something popped up on my screen. I'm just making sure I'm in the right location. All right. So one of the things that, to switch gears here real quick, is you have to be aware, especially in the HPC context, that Dask has settings, like a lot of complex software. And when you run Dask for the first time, it's going to squirrel away those settings in 2 YAML files that it will create for you in your .config directory of your home directory, dask.yaml and distributed.yaml. And these are, and you may want to actually tweak the settings. One of the settings you might want to tweak is something called the heartbeats. Every worker sends a heartbeat to the scheduler. And the scheduler will listen for the heartbeat. And if it doesn't hear a heartbeat within a certain allotted time, it's going to assume the worker is dead and reassign its current task to another worker. And as you might imagine, when you scale things up on Summit, we can have up to maybe 6,000 workers. That's a lot of heartbeats to listen to. So you go into this these YAML files, and you may want to dial up the timeouts so that you can give the scheduler a little bit more time to be able to listen for those heartbeats, so it doesn't actually accidentally drop a worker. Another thing to be aware of, you see the temporary directory there. By default, Dask will try to write stuff into your home directory. Well, here's some sad news. On Summit, your home directory is read-only. And the other sin it commits, it's a slow NFS file system. So those are 2 reasons you can't or shouldn't write stuff to that directory. So you set the temporary directory to be /10, which is local to the node that's running your job. So that's actually one of the other things that you might actually want to do. In any case, I would recommend looking into those configurations and tweaking them to get maybe a performance boost. I will warn you that the documentation is not very good for those. So you may have to do a little bit of trial and error. All right, so here's another thing that you might want to be aware of is if you know that the tasks are going to be there's a correlation between the size of the task and the time. You can leverage that by sorting the task into descending order by the size. So in this case with proteins, the more amino acids there are, the longer it's going to take AlphaFold. Fine, you sort in descending order, you pass that list off to Dask using the map function, and you can see on the right, that's a sample of 10 workers that it's like a Gantt chart. Those blue bars dictate how long it's been processing AlphaFold. And it starts out with long processes and gradually trickles down to where it's doing generally very, very small evaluations. And look at there, they finish within minutes of each other. And this is representative of the entire run. Now, it's easy to imagine if you didn't do this, that you could have a very pathological scenario where you have one worker getting all of the heavy loads, which means it's going to take forever to finish, and the other worker is going to finish a lot sooner, and the resources are going to be idle, which is something that we don't want. So how do we verify that the task ran or ran correctly? One recommendation I have here is that you can create something for called the Dask worker plugin, which is documented on the Dask site. And I would recommend assigning a logger there so that you can actually print out the arguments that are passed in, catch exceptions and whine about them so that you can become a little bit more aware of any problems that might be occurring. I also recommend writing out things to CSV files that you can get information from the run, like every worker has a UUID, what host was the worker on, what process ID. You may also want to capture the start and end evaluation times as a diagnostic, like things are taking too quick to run, things are taking too long to run. And also, if you capture the host name, you might actually be able to cross-reference that with the host names that were assigned to your job, so you can determine whether or not a host didn't get any work, which may be an indication of a problem with the scheduler. So those are just some other recommendations that we have for Dask for running on your particular HPC system. So Ada, AlphaFold, I think is in your ballpark.
Okay, so some of the things that we've been doing with these great Dask workflows is running, like Mark said, a bunch of protein folding, protein structure prediction tasks. So we get a whole bunch of different full proteomes. That means all of the proteins in an organism on Summit with the AlphaFold 2 workflow. Next. And the other thing we're doing is, again, these molecular dynamics replica ensemble simulations. And these are incredibly fast. We're running OpenMM, the program on the GPUs, and we've got 6 per node running. And you can see here, we've got 18 tasks on one node, 32 tasks on 2 nodes. The tasks are running very well. There's not a lot of wait time between them, but we do have a little bit of an overhead that's starting to build up. Next. And here's scaling it up even more, 45 nodes. Again, the same computational pattern, everything's filling in very well, but the overhead is now up to 79 seconds. Next. And then on 500 and 921 nodes, these texts have all completed successfully. The overhead is starting to get kind of significant, but it's still not too bad. These simulations can possibly run for hours if we want them to. And so it's not a horrible thing. What we're getting is an amazing amount of simulation time in just a few minutes on this. The next steps is testing right now. They're sitting in the queue, running on half of Summit and on the full Summit, about 4,000 nodes.
So we covered a lot of stuff, all right. Workflows using Dask have been run successfully on 1,000 nodes with 6 workers per node, so 6,000 workers successfully, and for several different workflows. So we know this is not an accident, it wasn't something special with one particular problem. This is actually something that's generalizable that we know works well on Summit. So, but we're continuing, as Ada just mentioned, to scale up to see if we can't scale up Dask to run on more of the machine. And it may be that as we approach exascale, we may have to split things up, take a divide and conquer approach, and have several different concurrent Dask deployments. Maybe have, because the scheduler is the bottleneck. It's the one that basically is the grandmaster that manages all the tasks and listening to all the heartbeats. And after a while, with too many workers, the scheduler is going to start tripping up and not performing. So we may have to shard the workload, basically divided up between concurrent schedulers, Dask schedulers. But very large workflows is a new area, and here comes Summit's replacement, Frontier, which should hopefully we'll have access to, knock on wood, that as Frontier comes online, that we will continue to scale our workflows to that much bigger machine. And with that, I thank you for your time, and I guess we'll be able to, we'll take any questions you might have.
Thanks, Mark and Ada. Virtual applause to you. And the first question is from Jim Edwards, and he says, on slide 20 and 28, you say that the data must be copied over TCP/IP. Why can't you use the system high-performance network instead?
Okay, actually, we had a slide here that we didn't show, which basically we do use the InfiniBand for Dask. And so it is possible then that you could send a very large model or data over to the workers using that. And I think that they're working on, the Dask folks are working on, was it the UX?
So yeah, so we use the InfiniBand, but unfortunately we're using the TCP protocol over the InfiniBand. So it's not as fast. So there's a UCX library that can enable Dask to use, the full IB protocol. And that is actually, yes, that's been implemented. Now, the thing is though, that you probably don't want to do that anyway, if you can avoid it. So Mark's workaround where each worker reads off of the file system is probably the best solution anyway. So, if you don't want to have to send it over the wire, no matter what the protocol is or the network, if you don't have to.
Yeah.
So is this a limit of a Dask or is it a characteristic of a Summit?
Yeah, I think it would be more, it's the Dask architecture thing, because that it sends the data to the workers and it has to get to the workers somehow, right? So it will send it over the network, and it's using the TCP/IP protocol, which generally is simple. And it basically uses something called Cloud Pickle to basically compress the Python objects and send them over the wire and unpickles them at the other end. And that's also very well supported by Python. But that's just how Dask does things.
Yeah. Because Dask is created for a heterogeneous type of environment. It could be used on the cloud, it could be used on HPC. And so that's what we're dealing with here. That's with this convergence. The UCX version of Dask has been implemented on Summit for things like distributed data frame analyses and database query. But the point is if you can avoid sending data out with Dask, it's better to just avoid it, even if you have a UCX implemented.
Thank you. So the other question is from David. What are the advantages, disadvantages of asynchronous many-task parallelization with Dask as compared to array or parcel?
That's a great question. And I know of Ray and Parcel, but I haven't had a chance to play with them. So I don't really have any comment that I could make on that. That actually might be something we might want to look at down the road. I've heard good things about Ray. I haven't heard as much about Parcel. So we might want to look at the performance characteristics between those two. But again, I can't comment on that. I don't know if Ada has heard anything about that.
I know that there's some benchmarks for Parcel where they focus a lot on task dispatch rate, just really getting many tasks out as quickly as possible. And they do beat Dask after you get to a certain number of tasks. We're not that concerned with task dispatch rate for these particular workflows because they've run for a pretty long time. But yeah, we are definitely looking into Parcel as something to compare.
All right, was that a question? Because I couldn't really hear.
No, I think that was background noise.
Okay.
Somebody, sorry.
Yes, it's fine.
Yeah. So thanks again for your very insightful talk. And with that, let's move to the next one. And maybe you will be available in the networking session later today for people that might have additional questions.
Okay.
Thank you. So the next speaker is George McCabe from Anchor, and it will be about a continuous integration of METplus use cases using GitHub Actions and Docker.
Hello, everyone. My name is George McCabe. As Dave, let's see here. Okay. My talk is called Continuous Integration of METplus Use Cases Using GitHub Actions and Docker. An overview, I will start by answering a question that many of you likely have, and that is, what is METplus? I'll then describe some of the challenges that the METplus developers faced with effectively testing the software. And finally, I will give an overview of the METplus testing framework that I helped design and implement to address these challenges and how modern software tools like Docker and GitHub Actions are utilized to make our jobs easier. So a little background information, in case you're unfamiliar, Git is a version control system used to track software changes, and GitHub is a cloud-based service that hosts Git repositories. A few terms I will use in this presentation include repository, which is a collection of files for a project with version history. A commit is essentially a snapshot of the state of the repository. A new commit will be created when new changes are saved. A push sends changes from a local repository to the cloud or a local Git repository to GitHub. And a branch is a named reference to commits to track related changes. And finally, a pull request is a request to merge changes from one branch into another. This diagram shows a commonly used development workflow called the Git flow workflow. The METplus team uses a slightly modified version of this workflow. The portion relevant to this presentation is circled here. The develop branch contains all the latest changes that will go into an upcoming release. Developers will create a feature branch, which starts as a copy of the develop branch's state. Changes are tracked by the feature branch, and when the feature is complete, a pull request is created. After another member of the team reviews and approves the pull request, changes from the feature branch are applied back to the develop branch. So what is METplus? The Model Evaluation Tools, or MET, were developed by the Developmental Testbed Center and first released in 2008. The tools were designed to perform consistent, reproducible numerical weather prediction model verification. The MET applications written in C++ are used to compare forecast models with observations to compute statistics and diagnostics. The tools have since expanded into a software suite known as METplus. Today, METplus is used by forecasters, operational centers, universities, and national laboratories all over the world, allowing researchers to speak a common verification language. METplus includes many components besides the MET applications. METviewer is a database and display system written in Java to perform deep analysis of MET output. METexpress is another display system intended for quick analysis queries. METdbload loads MET output into a database that is used by both METviewer and METexpress. METcalcpy is a Python package designed to perform additional analysis of MET output, such as statistical aggregation and event equalization. And METplotPy is a Python package used to generate images from Met output. METViewer and to a lesser extent METExpress leverage METcalcPy and METplotPy for the aggregation of results and plotting. As you can see, there's a lot of interactions between these components. I'm not pictured as an icon in this image, but theoretically everywhere in between the icons is the METplus wrappers. The METplus wrappers is a suite of Python scripts that build commands to run one or more of the various METplus components. The wrappers allow users to easily run the tools to process data for many runtimes without the tedious process of typing out each command or writing their own scripts to handle the command generation. Numerous calls to the Met tools that previously required multiple configuration files can now be executed using a single METplus configuration file. Each METplus component is highly configurable to meet the diverse needs of its users. Community contributions are also encouraged to extend the capabilities. However, this flexibility makes effective testing challenging. METplus is spread across multiple GitHub repositories so that users can easily obtain only what they need. Individual software components may be sufficiently tested, but changes may inadvertently break other components. Software dependencies required for one user's contributions may not be available in another user's computing environment. So the METplus team has implemented a continuous integration framework that utilizes GitHub Actions and Docker designed to address these challenges. This is just an overview of what's used, and I'll dive into the details in the following slides. There are over 100 use case examples that can be found in the METplus wrappers GitHub repository. They are provided to demonstrate various applications of the software. Users can copy and modify the config files to perform similar verification of their data. The use cases are also used to test the software with help from Docker. Docker is a platform used to quickly build, test, and deploy software using containers. Docker images are often described as a template or blueprint for a container. Docker is used to set up and isolate the testing environments to run each use case. Docker images are built from commands found in a text file known as a Docker file. A Docker file is read and executed by a Docker build command. This creates a computing environment by obtaining files, installing software, and more. A Docker run command creates a Docker container from an image. Additional commands can be run inside of the container. Directories on the computer running Docker can be mounted to the container. Here, a local directory named input is mounted. The contents of the directory can be found inside the container. These files can be used in commands run inside the container. Files created inside the container can also be made available on the user's computer. Docker images can be pushed up to Docker Hub, a web service provided by Docker, which makes them available to download elsewhere. Docker and Docker Hub are utilized in a variety of ways to set up and run each METplus use case. The Met tools are compiled into Docker images so that official releases can be made available to users, and development versions can be used for testing. The tools depend on a number of external libraries such as netcdf. To avoid frequently rebuilding these libraries, they are built and stored in a Docker image. The from keyword in a Docker file determines which image to pull from Docker Hub to use as the base. The Met Docker file obtains the libraries this way. Next, the Met applications are installed. This process makes it easy to quickly install development versions of Met used for testing. Nearly every METplus use case uses at least one Met tool, so the METplus Docker file uses the Met image as its base. Then the wrapper scripts are added. Each use case requires input data to run. The full set of data required to run all of the use cases is very large, so data is divided into groups. The use cases in the METplus repository are organized by category. Each category has a corresponding data set that contains all of the files needed to run all of the use cases in that category. These files are added to a Docker data volume that can be mounted to a Docker container that will run the use case. The input data volumes are stored on Docker Hub so they can be quickly obtained before running a test. A Docker create command is used to pull a Docker image and give it a nickname. Here is a Docker run command used to start a METplus container without any mounted volumes. Once the data volume is created locally, it can be mounted to a container using the volumes from argument. This makes the input data available inside the container. Many of the use cases can be run using only the METplus Docker container and the appropriate input data. However, some use cases have additional dependencies beyond the minimum requirements of the METplus wrappers. For example, many of the Met applications support reading the non-native data formats via a call to a user-provided Python script. So instead of passing files directly to the tool, a Python script prepares and serves data to the application. These Python scripts often require additional Python packages. Other METplus components such as METcalcpy also have additional Python package dependencies. Some use cases even utilize external software tools such as the GFDL tracker used to track hurricanes. Docker images have been created to isolate the different testing environments so that only what is required by a use case is available for that test. The Docker images used to run the use cases are created from another Docker file that runs a multi-stage build. In a multi-stage build, more than one from statement is used. Each from statement pulls images from Docker Hub. Some are given a nickname to reference later in the Docker file. The last from statement determines the base image to use. Select files from other images can be copied into the final image. In this case, the first from statement pulls the Docker image that contains the additional testing requirements, and the necessary files are copied into the final image. This approach improves the efficiency of the tests, as it is very time-consuming to install all of the dependencies inside the METplus container for each test. After the use cases have run, the output can be compared with files generated from a previous run that are known to be correct, which we refer to as the truth data set. The new output and the truth data are mounted to another container. The files in each directory are compared to ensure that the results have not changed. Sometimes differences are found that are expected. For example, developers may discover a bug that produces incorrect output, and fixing that bug may change the results. A newly added use case will also flag differences because the new output does not yet exist in the truth data set. When expected differences occur, the truth data is regenerated, incorporating the new data to use in future tests. Docker provides useful functionality to handle the complex process of testing the METplus use cases. However, there are a lot of moving parts involved, and it may be difficult to know when and how each step should be run. Fortunately, Docker integrates very nicely with GitHub Actions, a continuous integration and continuous delivery platform provided by GitHub. GitHub Actions workflows are defined in files that are checked into a GitHub repository and are automatically executed by GitHub Actions when repository events occur and the required criteria is met. Workflows consist of one or more jobs that are each run in their own environment. Each job consists of one or more steps that run shell commands or execute actions that perform common tasks. The GitHub Actions Marketplace provides many actions written by GitHub or third-party contributors that can be incorporated into a workflow. A commonly used action is called checkout, which is used to obtain code from a GitHub repository. All workflows can be reviewed from the Actions tab of the GitHub repository website. Red, green, and yellow icons show the status of each workflow run. Clicking on a workflow run will display a summary of the run. All the jobs are displayed here. Any artifacts, which I will cover later, are produced during runtime that can be found at the bottom of this page. Clicking on a job will display the status of each step within the job. Clicking on a step will display the log output for that step. The information in the logs are useful to determine the cause of a failure. GitHub Actions workflows can vary in complexity from performing small tasks like generating documentation to larger tasks like testing the METplus use cases. The METplus testing workflow contains rules that determine which events should trigger it. This workflow is triggered when changes are pushed to the METplus GitHub repository, or a pull request is created to merge changes into a branch. That is, unless the changes are isolated to the directory that only contains documentation. The jobs from the workflow will appear as checks in the GitHub pull request web interface, so reviewers can easily see if the tests succeed or fail as part of their review process. Workflows can also be triggered manually or by events that occur in other repositories. For example, changes pushed to the develop branch of the Met repository triggers a workflow that sends a signal to METplus to run the testing workflow. This makes it easier to determine if a use case has broken due to changes made in another repository. The first job of the testing workflow determines which other jobs should run. The type of event and name of the branch determine the default behavior to run. For example, push events on a branch name that starts with feature will run the unit test for the METplus wrappers in any use cases that have been marked to run. Push events on the develop branch will run all of the use cases. Pull request events will run all of the use cases and compare the output to truth data. Push events on the develop reference branch will run all of the use cases and automatically update the truth data volumes with the output. Workflows triggered by another component such as Met will run the difference tests to catch changes caused by other components as early as possible. Keywords found in the last commit message before a push may override the default behavior. For example, a developer can add CI run diff to the commit message before a push to their feature branch to force the difference test to run. This allows them to test that their changes did not break anything before creating a pull request. The job control rules are set in variables that are output by this job and read by other jobs to determine if they should run or not. Here, a job named job control has output variables that are referenced in another job named create output data volumes in the if keyword. If the value of this is set to true, then this job will run, otherwise it will be skipped. The next job builds the METplus Docker image and pushes it up to Docker Hub. This prevents the need to rebuild the METplus Docker image inside each use case job. The Docker Hub login credentials are stored as secret encrypted environment variables in the GitHub repository. The values for secret environment variables are hidden in the log files to prevent them from being exposed. Another job uses a custom METplus GitHub action to update the input data as needed. This action is found in its own repository. It compares files on a web server to Docker images on Docker Hub. If the data does not exist on Docker Hub, or the files on the web server have been modified since the Docker data volume was last created, then new data volumes are created and pushed to Docker Hub. This functionality makes it easier for developers to add new data to use in the tests. These two jobs are run simultaneously and both must finish running before the next set of jobs start. And this is an excerpt from the GitHub Actions workflow tab. Next, the use case tests are run. All of the use cases are listed in a file that describe what is needed to run them. The use cases are organized by category, which determines which input data set to use. The information for each use case includes an index, a name identifier, the path to the configuration file or files, and optionally a list of keywords that specify dependency requirements, such as which Docker environment is needed to run. Python scripts parse this file and build commands to set up and run the use cases. A JSON file defines groups of use cases. Each group will run inside its own job in the workflow. The use case jobs are run concurrently to speed up execution time. Each group is defined by a use case category, a list of indices, and as well as a flag to tell the workflow whether or not to run the group if only select groups are to be run. If the output should be compared to truth data, then that logic is executed within the same job. After all of the use case test jobs have completed, another job may run to update the truth data. The output from each use case group is obtained by this job using a GitHub action feature known as a workflow artifact. A workflow artifact is a file or set of files produced during a workflow. Artifacts allow data to be downloaded by users after a workflow is completed. GitHub provides an action to easily upload files as artifacts. Another GitHub action can be used to download artifacts that were created in a previous job, so these data can be accessed by other jobs. This workflow creates an artifact for each use case group that contains all of its output. Additional artifacts are created to help investigate issues. If any use case produces an error, an artifact will be created that contains only the log files for the use cases that failed. If any differences between the output and the truth data are found, then all of the files that were flagged are copied into another artifact so they can be downloaded and reviewed. So in conclusion, the use of Docker and GitHub Actions have provided many benefits to the METplus project. Continuously testing our software has improved our development process. We have caught many bugs that may have otherwise slipped through the cracks and are more confident that code changes will not have any unexpected side effects. This has made the team more efficient as changes can be reviewed more quickly and easily, allowing developers to focus on new development. It has helped define a clear process for adding new content so external collaborators can more easily contribute to the project by adding their own use cases or even improving the software itself. This testing workflow has saved the project time and money, but there's also room for improvement. The capabilities of the initial implementation were very basic compared to what is used today. The logic has been improved and expanded over time and continues to grow. Since the first draft of this presentation, it has been adapted to run for several other METplus components. And that's the end of my presentation. Thank you for listening, and I'll take any questions.
Thank you, George. I don't have any question now in the slide, so people please submit that, but I'll ask one myself since I have the mic, maybe two, if nobody chimes in. So the first question is about, you showed many moving parts in this talk, and I bet at least somebody will feel overwhelmed by that. And then, so the question is, how much of a learning curve is there? If somebody wants to start, with maybe the basics, is that something relatively easy? What has been your experience when you started?
Yeah, that's a great question. So as I mentioned, that the basic implementation that we originally had was much more basic than what we have now. So I would recommend, if you're getting started, to really start small and get something working, and doing some simple tasks, and then kind of expanding that as you go and improving things and make things more efficient. And so it started off as just running as, obtaining all the software and running a few of the basic use cases that didn't require additional dependencies or anything. And then they've since expanded to do a lot more complex things and perform a lot of the other comparison difference tests and all sorts of other things.
Okay, great, thanks. So the first question I have there is a comment that says from an early career somebody says, a great presentation. Can you please comment on the cost associated with your CI/CD pipeline? And I suppose the cost means cost in money, but I don't know if he or she meant something else.
Yeah, I can. So for public GitHub repositories, GitHub Actions is free. And so these resources are, as of right now at least, are free and can be run there. And if you have a private repository, there's a payment plan that I believe it's by data usage and time. And so, but in terms of cost of a project of getting started and getting the things running, this sort of iterative process has sort of allowed us to do that, as we don't have funding to just spend a lot of time creating this workflow. And so it's sort of done at kind of in tandem with other tasks that we sort of assessed the benefit of taking a little bit of time and getting this working in automation so that we could save time in the future. And it kind of was developed over a long period of time, but now it's in a good stable condition where it's been proven to be very useful for our project, and we've saved a lot of time and money in results.
Thank you. The next question is, how large is your test data, megabytes or gigabytes? And that's from Ed Hardnet. And I would add to that, what are the limitations from the size and computing power that's available for free, especially from GitHub?
Yeah, so the data that is many gigabytes. Some of the use case groups have input data that's close to 4 gigabytes. I'm not sure the exact amount of capacity that's allowed in these Docker volumes, but I know that we're getting pretty close to it. So far, each use case category has its own data set, and everything is able to be contained in there. But some of these use cases, especially some of the newer ones, we've been adding process data over, using climatology data. So it covers many years of data. And so we will likely be running into some of these limitations of how much data you can store, but dividing them up into different groups has made it a lot easier to manage. We would definitely not be able to put all of the data used for all of the cases in one area. It's far too much, unless it's on a local machine, but not in the automated environments.
Sounds great, thanks. The next question from Joshua Brown. Are any of the pieces of your workflow packaged as generic modular components that can easily be adapted to be used in other projects not related to METplus?
Yeah, I think it sort of depends on the project and what's going to be done there. But a lot of the components involving compiling the code and preparing data, a lot of those things could be leveraged. We've sort of taken this METplus wrappers workflow to test the use cases and kind of adapted them for some of the other components. And it really just kind of takes sitting down and assessing what's needed to be run and kind of understanding which pieces can be pulled out. But there's a lot of specific things that sort of need to be catered to a given project.
Sounds good. And then the last question I have, it's from Joshua Brown again. What in your experience has been the biggest pain point in creating CI pipelines?
That's a good question. I think maybe since there's so many different components and parts of this, it's difficult to to get things up and running and kind of working all together. Especially since things take a very long time to run. It's sometimes difficult to debug things as you can't really, some of the things you can't exactly test locally and push up there. It sort of needs to run in that pipeline, and it could work completely fine on your computer, but not up in the cloud. One of the biggest frustrations is there's, since this is sort of relying on a lot of different parts, that some things could go down that we're relying on that can cause problems. I know there's been some Python packages that had map files that needed to be downloaded, then the website changed and that was unavailable for a while. And sometimes, Docker Hub will go down for maintenance and certain things will fail and it's not clear what's going on. Luckily, a lot of times if you just restart the jobs, it ends up magically working. But that can be a source of frustration, is it's sometimes difficult to diagnose something that's going wrong. And to help with that, we've kind of added a lot of log information that's created. And then especially creating these extra artifacts that only contain the error logs, so that because some of the use case groups can produce a lot of output, and those are very large zip files that have to be downloaded. And so if you have a smaller file that just has the relevant information, that makes it a lot easier to download and investigate further.
Okay, great. Thanks. Virtual applause to you. And we have, hopefully you will attend a networking session later today where people may ask other additional questions. It was a great talk and great discussion. Right now we have a break and we will be meeting 20 minutes after the hour, so in 18 minutes from now. And we'll see you later. Improving. Hello everybody once again, and welcome to the Saturday session of the Improving Scientific Software Conference. Our next speaker will be Miranda Mundt from Sandia National Lab, and she will talk about a tiered approach to scientific software quality practice. And as a reminder, you ask questions in Slido. We'll post the link again into the chat anytime during the talk, and we will address them at the end of the talk. With that, Miranda, take it away.
Thank you so much. Hello, everybody, and thank you for attending this talk on a tiered approach to scientific software quality practices. As David said, I am Miranda Mundt. I'm from Sandia National Labs. I am a research software engineer in the Software Engineering and Research Department at Sandia National Labs. I have a background in mathematics and economics, and today we will be talking about scientific software quality. So, we all know in this day and age that expansive interconnected software ecosystems are a norm. Software quality in scientific software has a stronger emphasis than ever before, but software quality in its commercial form and all the forms that we're not used to seeing don't always fit scientific software needs. Software quality as well is not a one-size-fits-all problem within the scientific software realm. So, on that note, though, how does scientific software actually differ from commercial software? Well, in a lot of different ways. Number one is that it's primarily self-taught developers. Many scientific software developers actually have their domain expertise in some sort of science, like chemical engineering, electrical engineering, mathematics. As a result, they learned their software development as sort of an afterthought or through the job, on the job work, as opposed to in a formalized method. There are also unique challenges that scientific software developers face, such as requirements. In commercial software, requirements are normally well-formed and set up by stakeholders at the beginning, but very frequently in scientific software, there are no stakeholders at the beginning. There is research-directed funding that is geared towards getting a research answer. There's also issues in testing, in funding sources themselves, and in performance. Sometimes these emphases are different than they are in commercial software. And as a result, the end goal really for scientific software is the progression of science more often than the actual software itself. So what does this mean for our talk today? Well, at the in the Center for Computing Research at Sandia National Labs, which is where this Department of Software Engineering and Research sits, software quality was really not a standardized procedure. When it came to small projects like Oscar projects or LDRD projects, if you've ever heard those before, these projects the software quality for these projects were defined by their own project leads. They were left to figure out what quality meant for their project and apply it as they saw fit. While this problem was not this was not inherently an issue, there was a standardization problem in that there was no way to guarantee that there was at least a minimal amount of software quality that was being completed by all software projects within CCR. So in steps our department, we had a simple desire. We wanted to create a standardization framework for CCR. And I know most of you are giggling about the word simple there. Now, our problem, of course, is that existing software quality frameworks are really aimed towards commercial software. We can talk about ISO IEC, we can talk about CMMI, any of those frameworks. All of them are really geared towards big teams that have dedicated project members and that are able to actually put in time and funding to software quality efforts. So the question then for our scientific software teams, which range from 1 to 2 people up to 15 plus people, how do we really right size a framework? How do we make sure that we create software quality guidelines that actually fit the intended goals and the intended purposes of these softwares? So that was our goal. We wanted to create a tiered software quality framework that could scale and evolve naturally with a software project as it matured from its prototyping phases to a production level software. Our methodology that went into the creation of this framework had 3 parts. These 3 parts were interviews, surveys, and a rapid review. So in terms of our interviews, our motivation here was really based on a side project that we did. We mentioned it yesterday for Reed Milevich, who is doing a presentation tomorrow and is also attending this conference. He and I participated in a project to look about incentivizing software quality and motivating software quality in scientific software. As part of this, we found out that one of the big incentivizers for software quality practices was leadership, was having a strong advocate, a loud voice to say that it was important and to push it forward within the leadership community for your organization. So in our case, we decided we wanted to interview the leadership. So we approached every single department manager within CCR, that's 12 people total, the entire population of those managers. And we asked every single one of them to give us a 1-hour in-person interview. These interviews were designed to be very open-ended, with the goal to gathering answers to questions such as, what is your definition of software quality? What do you consider to be your process for quality? And what would be triggers for you to introduce more rigor to a project? How do your stakeholders enforce equality? And how do you measure the success of a project within your department? The second step was surveys for project leads and project members themselves. It's all great and good to have leadership telling you their ultimate vision, but we really needed to know what was happening on the ground within each of these individual projects. So we sent out an anonymous web-based form to all of the members of CCR. And this was a structured web-based form that was aimed at collecting information regarding project metadata, like the maturity and size, and perceived values of research and software development activities, as well as the current state of practice. This was completely anonymous and was entirely optional. The last thing that we did was a rapid review. So this is a systemic time-boxed literature review. It allows us to have faster turnaround at the cost of certain steps. For example, it's a more limited literature search. And normally, though, it's motivated by some sort of practical problem or some sort of practical answer that we're trying, or practical question that we're trying to answer. In this case, we had 2 unique research questions that we were exploring. Do different teams work better under different sets of quality standards? And how do we right size a software quality model? First, let's talk about the interviews and the results from that. So within those 12 interviews, 3 main themes really fell out. The 3 themes were fundamental research, triggers for more rigor, and non-prescriptive guidelines. So in the first one, we was really seeing that software is valuable insofar as it furthers research and promotes the trustworthiness of research results. So the main goal of CCR projects is really not the software itself, but the results that the software yields. Or as one participant said, it's clear that we are not a software development shop. We are a research development shop. This value itself also trickles into hiring practices. In the case, that is that most hiring managers are more likely to pick a candidate with a strong research background over a strong software background. The second category is triggers for more rigor. It was generally perceived that given the limited time each staff member actually has to dedicate to software development practices, That time needs to be carefully spent. For a project which is new and trying to prove a novel concept, the rigor behind software quality is far overshadowed by the rigor required for the validation of the research results itself. As one participant said, until we really had a sponsor that demanded a higher level of rigor, like process documentation traceability, there really had to be a clear benefit for all of us in order for us to do them. So as the project matures, though, most of these participants agreed that the scale can kind of tip in the opposite direction. It can go more towards software than it can towards the actual rigor of the research results. Commonly paired with this comment, though, about rigor was also expertise. The biggest help that most existing projects could really benefit from was access to a dedicated software engineer, particularly when the software was going through a maturity transition. Before this transition, though, the software likely existed to answer a research question and really only needs a basic amount of software quality rigor and a larger dedication to the validation of the actual answers. The final category was non-prescriptive guidelines. So many projects within CCR fall under the Advanced Simulation and Computing Program and its associated software quality plan. If you've never heard of ASC or this before, this is an open source document. You are welcome to go and find it. It is also linked in the accompanying paper for this talk. But the intent behind this plan is to allow projects to define their own processes while providing a guideline for what those processes should be achieving. That is, rather than explicitly stating the exact tools and procedures to use, the ASC quality plan outlines general process areas which must be considered and addressed. As one of the participants stated, when I had my first ASC software quality assessment, one of the reviewers told me, we're not here to expose external processes for you. You get work done, so therefore you must have processes. So software quality as well, as a note, is still an open question in certain realms of cutting edge computing. So requiring extremely prescriptive practices was extremely unreasonable. The next step in our methodology was the surveys. We got about a 7% response rate of these surveys, so about 15 out of 200 people within CCR. The biggest gap, obviously, that we can see from this data is that we had no respondents from the proof of concept level of maturity. We had quite a few coming from the somewhat productionized level. But what we can see from this metadata as well is that in terms of the team sizes, the maturity, the number of people with software engineering training, it really matches the literature that's out there about scientific software, that most of the teams are small. And of those small teams, very few people have some sort of formalized software engineering training. This survey also had a portion, in addition to the metadata portion, asking about end products and the perceived importance of those end products. Those products were broken into two different categories of non-software or more research-oriented end products, and then software development activities. So as you can see on the left side, we've got publications, presentations, and research answers. We can see that particularly in the realm of presentations and research answers, we get high values. We also get relatively high values in publications, though somewhat higher in the presentations and the research answers. In terms of software development activities, we asked a variety of questions in different categories. In order to make this information more accessible, we grouped those categories of questions in our final analysis. And as you can see below, what was grouped into those is listed together. But what we can see is that there's actually quite a bit of emphasis on software development lifecycle considerations. They're considered to be generally important, whereas testing is seen to be not necessarily as important. And user and stakeholder considerations has a pretty even spread. Now, what we decided to do with this information was to kind of build this into our framework to make sure that we were matching the importance that is perceived by those who are within these categories. Our last piece was the rapid review. This is a very big table. It's a lot to digest, but I'll give you the kind of key takeaways on this. So this rapid review, how it was broken down, was try to answer those two research questions I mentioned earlier. What fell out of it was 6 different relevant factors. Those factors are individuals, teams, organizations, technology, process, and customers. And besides in the case of customers, where there was some information, but not really a key synthesis takeaway, we got large takeaways from each one. For example, in individuals, a scientific software developer who has received formalized training in software development will ultimately create higher quality code in a more productive manner. So what is that saying? It's saying that if you have training, you're more likely to make quality. Kind of makes sense, right? In terms of teams, good teaming enables productivity and quality. In terms of organization, in order to achieve productivity and quality, a project must be in alignment with an organization's values and processes. But the organization or funding source must also value quality and allocate funding towards quality activities, which is a common issue as we see in most scientific software realms. In terms of technology, the right tools can be used in the right way, can actually improve quality. That is, technology can both enable and inhibit quality depending on usage. And then in our last big key takeaway was in the process area. So adherence to a managed and well-defined process for software development is likely to result in quality and productivity. Now, these three different categories of research that we did within our methodology ended up resulting in our tiered software quality framework, which we can now see on this page. Again, a lot to digest. I'll try to break it down for you. So the first thing to note is that we had 4 different tiers, and these tiers were meant to be determined by a project lead. So a project lead is intended to go into this table and to compare the characteristics of their project, those listed in the table for the appropriate tier. As you can see, it goes from level of least maturity to most maturity, also incorporating ideas about risk, because at least in the national lab scenario, we do have to consider risk factors when we're considering how much rigor to apply to a project. So we can see in tier 1 that these are new projects. They're in early stages, they're small, they have short-term funding, and they're very exploratory. Now we go all the way up to tier 4, and these are these more established projects that are very mature, they have regular team members, and they are productionized and released on a regular schedule. Now, for each one of these tiers, the tiers have requirements. Now, these requirements in the way that we structured this are exactly as they sound, required. So they are the minimum activities that are required to be done for these different levels. They go from very basic at that top level, so making sure that you have version control, some level of requirements development, though this can generally be changed based on the more traditional version of requirements development. Because more often than not, you don't really have stakeholders. So you're just trying to make sure that your requirements fit the intended use of your software project or your research project. And they also require things like a backup plan, like where are you backing up your data? What are you going to do if you have a catastrophic failure? As you scale up in those tiers, those requirements become more rigorous. So for example, when you get to tier 3, this is where you really have to start thinking about things like end user documentation and developer documentation. You have to consider design and actually putting more intent into your design as opposed to more ad hoc design considerations. You'll also notice, though, that there is a recommendation category. The recommendation category is really meant to be based on intended use. So something that we baked into this framework was the idea that based on the eventual intended use of your software, you might need to implement rigor earlier. So if you have a software that you're developing that you know, even from an early stage, is going to end up being semi-productionized to productionized, you know that there's going to be people outside of your organization or your immediate team who want to use it, you will probably want to implement rigor at an earlier stage. Many of the recommendations end up becoming requirements in later stages. So the way that we phrased this for our project leads was based on your intended use. If you know that this is going to go to a larger subset of people or a larger set of people, maybe apply those recommendations at the recommendation tier instead of at the requirements tier. Now, of course, we had some threats to validity to this actual framework itself. The framework was released in late 2020, which, as you can probably guess, was right in the middle of COVID. So we didn't really have a way of actually making sure that there was, strong enforcement. We didn't really take into consideration the fact that we released this during the peak of COVID restrictions, and we didn't make any changes to it because everything was virtual anyway. As a result, though, we don't really have very reliable data as of right now about the adoption and efficacy rate, and this is something that we really need to look into in the future. In terms of the interviews, there are several levels of managers within CCR. There's level 1, level 2, etc. So we interviewed all the level 1 managers as the ones who were closest to the actual project leads. But it was very possible that we missed some larger level requirements that might have been there from a higher level management or a higher leadership position as a result. The open-ended interviews as well made quantitative extraction of data difficult. So as you can see, three major themes fell out, but there were a lot of smaller themes that came to fruition as well from these interviews. From the surveys, we did get a reasonable response rate, but as I noted earlier, there was a lack of response from the least mature category. This means that our synthesis of this information could possibly skew towards more production ready values as opposed to those values that might be represented by those least mature or less mature categories. There was also no information on those current practices for those least mature, so we're not 100% positive that tier 1 is appropriately right-sized. In terms of our rapid review, I mentioned it was a rapid review, it was not a fully systemic review. So it omitted some certain steps like an extensive literature search and also had a lower quality appraisal bar. We are, however, fairly confident that this is a low risk category of threat to the validity, considering that we still did grant a very large number of literature or pieces of literature for this. In terms of future work, I mentioned we haven't done any sort of analysis on the efficacy of this. So there would be some great avenues for efficacy and reproducibility of this framework creation process. It'd be great to do some case studies outside of national laboratories themselves, like in academia, which may also benefit from having this right-sized scaled framework. There may also be some quality. There may also be some benefit in mapping mapping this framework to commonly recognized measures of maturity or quality, such as technology readiness levels or some existing frameworks like ISO IEC 25010. There is also the possibility of integrating actual research quality guidelines into scientific software quality framework. There's a senior scientist within CCR who has a research quality documentation or framework that she has created for members who do research within CCR. And we are actually looking into integrating that into the software quality framework and seeing how those two things mesh and combine appropriately. So to finish us off, remember our motivation today was that we wanted to provide a set of software quality assurance guidelines for scientific software developers. Our key question being, how do we right-size software quality for scientific software projects? We used interviews, surveys, and a rapid literature review to gauge value, current practices, and recommended practices for those within CCR. And then at the end, we created a tiered framework that scales and evolves naturally with a software project, which hopefully will promote implementation and allow people to have at least a predictable amount of software quality within their scientific software projects. And that is it. So it is now time for Q&A.
Thanks, Miranda. A virtual applause to you. That was a very interesting talk. And the first question we have is from Shahzeb Siddiqui. I hope I'm pronouncing your last name right. Do you think research groups can benefit from hiring at least one good software developer to improve software quality, even if she is not familiar with the technical aspect of the software product?
That is a great question, and my overarching answer will be yes, absolutely. Scientific software or software engineering is in itself a domain expertise. And when you're talking about particularly scientific software projects, you already have domain expertise in whatever the technical realm is, whether it's chemical engineering, mathematics, whatever. You have that expertise there, so why not bring somebody with that other domain expertise into the equation? It is helpful if they have some sort of background in that. So that's actually what RSEs are. If you've never heard of a research software engineer, the kind of idea about a research software engineer is someone with a subset of that background information so they can have a more technical conversation even without knowing all of the ingrained details. But absolutely, it is a great idea to hire at least one good software developer.
Thank you. Next question from Christina. And I say, Miranda, this is a wonderful presentation of this type of data. How would you suggest we start working toward assessing our group's need within this framework?
Another really great question. Thank you, Christina. So if you're in the situation where you have an established project already and you're trying to figure out, or if you have a group with established projects and you need to try to create this framework that is right sized, I highly recommend following a similar approach that we did, where you get a good gauge on, what is leadership value, what do they see as important, and also try to figure out those the current workflows and the current steps of your groups as they exist right now. That way you can try to make sure that whatever you're creating is really just formalizing practices that are already in place. Because as I noted, most projects already have some sort of processes and workflows that they're doing. They just may not necessarily know why they're doing them or if they are in fact the best method for doing that practice. So it's really just a formalization of that. So I would highly recommend doing some surveys, doing some interviews. There's a lot of literature out there. We have a publication or a technical report out about incentivizing software quality practices within scientific software that you can reference as well. But yeah, that's probably a good approach.
Next question from Reed Milowitz. Many projects start out small, proof of concept efforts, only to grow in size and find the original software quality practice to be inadequate. How do we reach this project earlier in their life cycle?
This is actually an entirely one of the big motivating factors in our work itself. So one of the things about having a framework like this, right, is that we surmise that it is only as effective as it is enforced. So ideally in those scenarios, what you really want for those like smaller projects is to have somebody who has more expertise come in earlier in those projects to advocate on those best practices, or to at least provide resources. Something I didn't mention in this presentation, but that we have provided to the project leads within CCR is we have a website that we have set up with all of this framework nicely lined out and easy to use. But in addition to that framework, we have a resource list that points them towards all of the resources that might help them with these different activities. So, you know, having somebody that they can consult with as well in the software engineering and research department, which is one of our purposes, is really quite valuable to those smaller projects, because they may not have funding to hire somebody for a long period of time, but they do have time to dedicate an hour to talking to us and to looking over this resource list and finding those pieces of information that might help them point in the right direction and help them to scale appropriately as they grow.
Thanks. And since I have a question which is in between the one you just answered and the next one, I'll ask mine first. Sorry for hijacking that. But it's, is this website available, and does it include, you know, any kind of advantages for the team, you know, especially at the earlier stage? You say, well, we have a process already, like you said, and so why we should change what we're doing so that they achieve a benefit for themselves, rather than being just mandated from the top.
Absolutely. So our website is internal because it is a collection of internal resources specifically geared towards Sandians. That being said, we do have some talks about trying to make some sort of generalized resource available either on one of like a bigger website like BSSW or on the US RSC Association website. Those are in talks that, of course, they're not available right now. But to answer your question about, you know, those smaller scale, I mentioned this, but something that the software engineering and research department at Sandia National Labs does is provide consultations. They're, you know, short 1 hour, 2 hour, however long is necessary for those projects, to talk to them about their processes as they exist right now, and hopefully point them towards the direction of either improving those processes or giving them resources to I apologize, my cat is trying really hard to get into the screen right now, but trying to promote better practices and also inform about how they might get more information. Something as well, those of you who are interested about, you know, process improvement, tomorrow, Reed Levitch, Elaine Rayborn, and I are hosting a PSIP tutorial. PSIP is one of those process improvement workflows that we recommend that people try if they're actually thinking about doing incremental small changes to their processes. So if you're interested in learning more about that, come to our tutorial tomorrow. Plug.
Great. We have another question from Joshua Brown. What do you think is the lowest hanging fruit that is not being used by the lowest tier? I would hope version control is pretty ubiquitous, though Janine's talk yesterday made me wonder.
So that's actually kind of the intent behind the design of our lowest tier, is really to hit the lowest hanging fruit. So we think at the lowest tier that at least from the interviews and the research that we did, the lowest hanging fruit seems to really prioritize, right, those research answers, the answers to those research questions, and just trying to see, you know, dartboard, can I even get this idea to work? As a result, the biggest importance for them then is retaining the information that they have. So version controls, backup plans, data management, all of this I think is actually the most important, just from the interviews and the background that I did for those lowest hanging, those lowest tiers, that lowest hanging fruit. And you would be surprised, more people than not, well, more people than you would want, are sending emails to each other with version 1, revision 2, comments 3, as opposed to actually using a solid, version control system. So that really is, I think, kind of the most essential thing is data management and data retention.
Thanks. There is no other question in the chat, but I will ask another one related to that. And is I didn't see many people these days sending those emails, but I've sent very many doing that maybe 10 or 20 years ago. But what I've seen these days is people using version control by using it sort of like they were using emails, so that not effectively, let me put it that way. So do you have any suggestions about that?
I do. Yeah, and it all kind of goes back, something that if you read enough of my papers or go to enough of my presentations, you'll find out that I'm a huge advocate for training and for personal resource growth and personal development for all of these scientific researchers, because it's all great and fine to have a really good software developer in there to make some changes and fix some things, but if nobody else is following that process and nobody else has that kind of lowest hanging fruit information or knowledge, you're gonna have a hard time actually making that persist even after that software developer is gone. So within Sandia National Labs, actually, we've offered Git training, so intro to Git, and trying to help people get that kind of base foundational knowledge for how do you use Git and how do you use it effectively in your everyday development. So really, I think that the key thing that you can provide there for people who maybe aren't using it as effectively, but are kind of using it, is resources and training towards showing them what is a better way to do it. It might take some time because a lot of those people are very ingrained in their current workflows and their current processes, but it really is kind of a showing you how much easier it can be and how much better it can be, but also giving them the tools. As I noted, tools are only as useful as they are being used properly. So you really need to teach about the proper use of the tools to expect people to actually use them as intended.
Sounds great, thanks. And with that, we are almost at the end of the time. Oh, great talk and great discussion. If any of those are available publicly, maybe send them to the chat so people might leverage your efforts. And after that, let's move on to the next speaker with after another round of applause to you.
Thanks, everyone.
So our next speaker is Shahzeb Siddiqui from Lawrence Berkeley National Lab, and he will talk about Spack infrastructure at NERSC.
Okay. Can you hear me?
We can hear you, but we don't see your screen if you are supposed to sharing.
Yeah. Seems like I can't turn on my video. It says the host cannot allow me. It's weird.
Do you want to use this? Okay. Yes, now we see it. Perfect.
1 second. Oh, okay. Can you see the screen?
We see your slides and we see the small square with yourself.
Sorry. Yeah. Oh, okay. Yeah. Okay. Okay. Thank you for attending this talk. My name is Shahzeb Siddiqui, and I work at Lawrence Berkeley National Lab as a HPC consultant. So I'm in the user engagement group at NERSC. So what we do is we support our users with user documentation, training, consulting support. Also, we provide like a lot of the software that's available on our systems. So for this talk, we're going to talk about the Spack infrastructure and how we use Spack to deploy software at NERSC, and give you guys some idea of like how you could probably use something similar to deploy software at your site. So let's get started. Okay. So what we'll be discussing today is how we use Spack to deploy what's called the extreme scale scientific software stack, which is called E4S. It's basically a subset of Spack packages, like a lot of the popular open source like HPC software that you see. It's about it comprises of like compilers, data and viz tools, math libraries, and all sorts of really useful stuff. We will use GitLab to automate the software deployment process. And I'm going to talk about how we do the software deployment at NERSC and some of the best practices and how you could potentially use some of these same things if you don't have a deployment process. So we'll talk about, if you don't know what Spack is. So Spack is a package manager for HPC that supports installations of multiple versions of software. And they can be, tuned to the system. So everything is being built from source. Okay. E4S is a community effort. It provides, open source software package for developing and running scientific software. E4S is provided as a pre-built container. They also have a build cache. You can also build it from source, which is what most facilities do, and that's what we do also. Okay. So it's released every 3 months, E4S. And what we do is whenever there's a new release, we will try to build as many of the software on our system. Okay. So the one main motivation behind this project was that we needed a way to automate the entire deployment process. So what we decided to do was use GitLab to verify the deployment, and it is fully reproducible. Because in the software deployment, there was many steps that we had to do, and we didn't want to make sure that there was any kind of error in the step. And in order to make sure that the deployment worked correctly, we had to make sure that the whole software stack builds from source. So GitLab was just natural fit because we had GitLab and we had runners set up on our system, so we could just just stand up a project and just start building. The other main thing was that we were building a really big stack, and we needed to accelerate this deployment process. So, there was about 100 plus root specs, so in Spack, but, it turned out to be like 400 or 500 packages, and we wanted to get this deployment time down to within a week. Currently, it took about like 4 to 6 weeks trying to go through all the build errors, and there was no automation. You just had to go on the command line and try to see all the builds. We wanted a single repo for all of our Spack configuration because we were doing multiple deployments. So we didn't want to reinvent all of our Spack configuration. We just have it in one place. So it made it easier for us to do future deployments. And also we needed a GitLab runners for all of our systems so that we can do these deployments properly. And one key distinction is that we wanted to have at least one single user that would do the deployment, because doing the deployment with different users caused all sorts of weird issues with user environment. So we stood up basically a runner with a single user so that all the deployments are done with a single user. Okay, so with that, I'm going to introduce the Spack infrastructure project. It is open source. It's available on our GitLab server, but we have a push mirror on GitHub, and then there's also read the docs. So NERSC Spack infrastructure, read the docs.io. So this contains all of our Spack.yaml that we use for our deployment on Cori and Perlmutter. As I mentioned, we use GitLab to perform basically full source builds of the stack and also the full deployment pipelines. So the actual production pipelines are in the same, basically they could just be leveraged through GitLab and it would just run it. Okay. So I'm going to talk about our deployment process and how we do it here at NERSC. So first we acquire this Spack.yaml. It's provided by the E4S team with a reference Spack branch. We port our Spack configuration, basically the Spack.yaml with a compilers, package preference, and then we build the entire stack. And that step 3 is what usually takes the longest time because we have to go through all the build errors until all the packages are built. Sometimes we provide a build cache. So if you're providing one, then you have to sign all your packages with the GPG key. We obviously generate the modules. the users see, and fix any module conflicts that you may have. We do the deployment in the production path, or whatever that path that you decide. We create a user-facing module so that in this case, we call it E4S. And then we write the user documentation so that obviously users can see. This goes through a peer review process. We publish our Spack configuration in a project called Spack configs repo. And then there is a facility dashboard, E4S facility dashboard page, which shows all of the E4S deployments. We just update that, and I'll show you in the next slide. And then once we're done, we actually just send a weekly, basically communicating in our weekly email so that the users know about the stack. So I'm going to show you what this step looks like a visual representation with all the steps. So first is we go to this E4S project, and they're the E4S project organization. There's a project called E4S, and then typically the team will provide a spack.yaml for the release. So we just take that spack.yaml and then we port it to our system. So step 2 is basically figuring out what compilers we support and setting those compiler definition, and then all the other things that are related to getting Spack work at your facility. So deciding what packages you want to install, and the preferences, like what MPI you want, and which variants you want. So all of that stuff. Then we do the whole build, and we do it through GitLab. And basically what it is just we press play, and one of the pipelines will run and do the whole deployment. We generate the modules. So the user-facing modules that basically generated by Spack. So we would create the user-facing module. So in this case, E4S module when we do the deployment. And then we have a page per stack whenever we release the software stack. So in this case, E4S 2202, which was actually released basically like in like the week of March 16th. So we write the documentation so that once it's available, we then announce it to the users. We update this facility dashboard, which kind of just shows you all the E4S deployments, and anyone can contribute to this page. Basically a summary of, which system had E4S, number of packages that were installed, which version of E4S you used. We share the Spack configuration upstream. So I just showed you like a pull request that I put, and then we announce it in our weekly email. So this was just an announcement for the 2202 stack that was released on Corey. So yeah. So for our GitLab, we actually have shell runners. So we use a single user called E4S. It basically runs pipelines on our system. So we have Perlmutter and Corey, which are our production system, and Muller and Gertie are TDS systems for basically Perlmutter and Corey. So these are runner names. So basically we had to configure our project to have these set up so that we can run jobs. Now I'll talk about what the actual deployment looks like. So this is actually a deployment on Perlmutter E4S 2111. And what you want to take away from this is one of the things that we found is that in order to have a clean environment, we created a virtual environment, basically a virtual environment from just virtual environment. So Python-mvm. We create the environment. We have to install Klingo in order for us to use Spack, and then we try to do basically the setup. So we're trying to the root of where we're installing E4S. This is defined by the E4S root variable. We remove Spack and then we clone Spack. So this is one of the branches of Spack that we basically the release that E4S provides. So E4S 2111 is the release branch. We create an environment called E4S with a spack.yaml that's in our repo. We activate the environment and then Spack install. And that red step is going to take a long time, but it will do the whole install. We generate the modules. So Spack module tickle refresh and lmod refresh, that does the module generation for tickle and lmod modules. And then all this stuff in yellow is just basically just debugging, but making sure that the Spack find shows the output and the modules are generated properly. So we just do module use and then module avail just to see if the module files look correct. Okay, so I'm going to talk about, so one aspect of obviously the deployment is getting the module files set up properly, because most HPC sites support a module tool. So for Spack, this can be done. So they support both lmod and tickle modules. So for Perlmutter, which actually uses lmod, we generate both. So in order to generate lmod modules, you have to define an lmod property. That's that in red. And we don't have any hashes. So hash length 0 means don't generate modules with hash. Now, blacklist implicit is a really useful feature. Basically, it tells don't generate modules for all the dependencies. So with Spack, you're going to get like, you may install like a package called Petsy, and it may have like 30 dependencies. With blacklist implicit, it says only generate for the actual root specs and not the dependencies. So you may only get one module file generated as opposed to like 20 different modules with utilities that users won't use. So we always use blacklist implicit equals true. For the lmod hierarchy, we do an MPI hierarchy. For all environments, we set a root called basically the name underscore root to the prefix. So a user can just go like, if they want to see like Petsy's root, they can just say Petsy underscore root and they'll find the prefix, which is the root installation. And for, let's say, for instance, the tickle modules, you have this tickle key. And for the naming scheme, we use the name version compiler name compiler version. So what that shows you, if you look on the output, that's the first one right here. All the modules have the name version and then the compiler and the version. Now you may notice that some module files have -mpi -cuda. That's to indicate that a module, that package was built with MPI. Like for instance, Hyper is built with MPI plus CUDA. So we can actually define suffix and what we call MPI and CUDA for all the modules that are built with that. And then for the lmod hierarchy, the way it works is you generate the compiler module. So you see GCC 930, and it shows you the hierarchy only for the GCC stack. We also have NVHPC, but you don't see it. You have to load NVHPC and then you see the other stack. So that's what the hierarchy in lmod does. So we provide both for users. Okay, so I'm going to talk about the GitLab pipeline. So in order for us to do the deployment, for let's say this is for the CI pipeline for Perlmutter. So we test the stack without impacting production. So in order for us to do that, what we do is we have a schedule pipeline that runs, and you can just press play. So you see this like this schedule pipeline right here in green. You can press this play button, and it will do the whole deployment. The way we set up our pipeline is since there's many scheduled pipelines, we have this unique variable called pipeline underscore name, and we specify the name of the pipeline that we want, the name of the stack that we want to do. So our naming convention is the system underscore E4S underscore the version. So in GitLab, you can do something called rules and define what rules conditions allow the job to run. So it says if it's a schedule or if it's a web interface, and if the pipeline name is this Perlmutter E4S 2111, then only run this. What we have done is this value Perlmutter E4S 2111 is actually defined in the schedule pipeline, but you can also do it through the web interface. So what that means is that if you want to just run the pipeline manually, you can just go in and do it through the web interface without having to wait for the pipeline schedule, which could be whatever you want, and still do it this way. So that's the whole idea behind this. And obviously, we can also trigger the pipeline based on push. So if you do it on push, we have it set to basically the path to where the spack.yaml is. So if there's a push commit which changes files, which changes the this file, it will also trigger the pipeline. So now for the production use case, we have to think about how we're going to do this. So first of all, the way we decided is that we can only trigger the production pipeline through the web interface. It didn't make sense that we would commit this, we would trigger the production through a commit or even a schedule pipeline, because the production will only do it once whenever you think it's ready for release. We still use the same thing called pipeline_name, but the naming conventions that we use basically _deploy for all of our production pipeline. But there is an approved job that actually is a manual job that needs to be approved by an administrator in order to run one of the production pipelines. So this GitLab job called approve will check for the condition if it's a web and basically a list of all the production pipelines. In this case, there's 2 production pipelines. And then in this case, if that manual step is approved, then the Perlmutter 2111 prod pipeline will run. Okay, so now I want to talk about kind of the deployment structure or file structure that we have. So we have a shared project space, global common software Spack ECP. This was kind of our layout for the each stack. So we first had just a subdirectory called E4S version. It worked well for the first 3 releases, but then when we introduced Perlmutter, so for the first these first 3 versions were for Cori. But then when we introduced Perlmutter, we realized that we needed to organize by system. So then we have Perlmutter and then Cori, because that way we can then we won't have conflicts. Each stack has a subdirectory called software, where the root of all of our software is installed. A directory called modules, that's where all the module files are, and then the actual Spack instance that we cloned. So I'll give you some like best practice for software deployment. So one thing is you may want to have a formal directory structure where you deploy software. Don't have one stack, but plan on having multiple stacks throughout the lifetime of the system. So whatever that may be, like 3 to 5 years. If your file system is shared between HPC clusters, so if you have more than 2 clusters, 2 systems, then you may want to think about having it organized by system. So let's say if you have GPFS, some root, and then have system, the name of your system, and then like a version of E4S or whatever you want to call it, that may work. You may want to consider having a software stack behind a meta module. So what that means is a module file that says module path. Instead of actually adding the module path at startup, startup meaning like when the user logs in, they just see everything. What this does is it avoids the situation where user scripts get broken due to system change. So somebody has a script that says module load Python, and you make the change, and now your Python is changing. All of your user scripts are broken. If you tailor it so that it's behind a meta module, so that they load a stack and then load Python or whatever it is, their scripts are less likely to break. You want to avoid having an explosion of modules, because Spack definitely does that. Blacklist implicit is a really good way of cutting down on the modules. It only generates for the root specs. You want to avoid having hashes in module files. So instead, you could use suffix. So what we use is MPI and CUDA, and that's really applicable for most of the software. And you can have as many suffixes as you want. The idea is that you want to avoid module conflicts. So if you have like 2 instances of the module file with the same name version, you need to have some unique name. You should consider having a single user to deploy the stack. So if you're doing it in CI/CD, consider having a process which does a full source rebuild, and you should have at least some CI tool like GitLab or Jenkins or whatever you have at your site. You want to make sure the stack is world readable and it can be accessed by everyone. So something like a UMask 002 kind of helps. And then have some kind of strategy to deprecate your stack, like some kind of support plan, like a year to like 18 months or something like that. So yeah, this is my last slide, but yeah, consider having some kind of a robust software deployment process. So that you can use this process to deploy your software stack on all of your HPC system. So it would be really helpful to document this software deployment process so you can internally use it, train your colleagues, and consider having like a few individuals take ownership of this task, because this is a key task. You're basically providing the whole software stack for all of your users. So if you have 2 to 3 individuals, they can perform this deployment on all of your HPC systems in parallel. Consider having some kind of automated process. Use some existing CI tools like GitLab, Travis, or Jenkins, or whatever you have. So Spack is not the only way to deploy software. You can also use containers. There's a thing called like Easy Build, Conda environments, or even the NVIDIA GPU Cloud, which is the NGC containers, or even like Bioconda. That's all I had. And yeah, I just wanted to give acknowledgement. And I'm open for questions now. Thank you.
Thanks, Shahzeb. Round of applause, virtual applause to you. And we have a few questions. So the first one is from Miranda, and she says, step 3 states build and work through errors. How long does the process of working through the errors generally take, and are errors expected?
Can I see the question? If you can screen share. How long does the process of build through the errors generally take, and are errors expected? Yeah, so I can give you for our most recent deployment that we did on EFROST 2202, we did the whole deployment in 2 weeks. It took about 1 week to do basically work through all the build errors. So it was. When you get build errors, you have to go in manually and troubleshoot all the errors and try to try different ways to install the software. The approach that we took is we tried to simplify the troubleshooting process as much as we can by trying different. So obviously you have to look at the logs, but if the bug can be resolved through different, like say, change the compiler, change the version, try different variants, we try all of those steps first. If it's outside the scope where it's like, okay, well, you have to report it to the Spack team, we just skip the package and just go to the next one. We don't try to, get too bogged down on one specific package because we have to like just deploy the stack. We document the error and then we just even just report it to Spack. Hopefully that answers your question.
I think it does, but she's around and she can give some feedback. Next question I have is from Brian van der Wind, and he says, do you currently encourage support user to build their own software with Spack? If so, do you provide any infrastructure for that?
Yes, we do. We recommend that the users actually install software through their own user account. We actually set up our Spack instance such that Spack will automatically install in their user accounts. We also provide a build cache for them. So if they want to reuse the software, they can actually do that. In terms of the like the infrastructure, I think we want to have a little bit more training at NERSC. So we're going to try to develop some material for user documentation, if that makes sense. So I just wanted to show you where it is, but this is the NERSC Spack infrastructure. It's on read the docs right here. And the idea is eventually we're going to expand on this user documentation with the, can you see my screen?
Yes, we can.
Okay. Yeah, so we share all of our Spack configuration here. Basically, you can just like copy paste this if you're on our system and run it. But we want to have at least a training material, and hopefully we could then use it to help users. Yeah.
So since you mentioned the build cache, does it mean that users using, installing additional software with Spack need to reinstall whatever you install it in your global environment, or they can layer on top of each other? Because that's a kind of a pain point in Spack, right?
Most of the times they have to reinstall, but if it's from the build cache, it would get installed obviously in their user environment. This is actually our link to our E4S page, and as I mentioned, we have a documentation per stack. So this is like the 2202 release, and as part of the developer workflow, we actually kind of walk through how users actually go about and set up Spack. This was on Corey. So if you're using a really recent version of Spack, you may know that Klingo is one of those things that needs to be used in Spack. So one of the workarounds that we have is we have a shell script, which is basically installs Klingo for you in a Python environment, as opposed to Spack doing it, which sometimes actually fails to do it. And then in order for you to actually use Spack, we recommend users just create an environment in their home directory or something. And then, yeah, we have a simple spack.yaml, and then you just Spack install, and then, here it actually installs Pappy. You can see the output right here. I was able to install this software. We can generate the modules for users. So what happens is it generates the module, and you can see if you ls into this directory, you see Pappy is generated, and yeah, you can regenerate the modules again, and then you can see now we have like actually 2 versions of Pappy, and then you can see the module files right here.
That sounds great. We have 3 more questions, but since we are to the end of your allotted slot, and the next session is a networking session, I suggest, with consulting with the other conference people, that we continue the discussion in the networking session. I don't know if we can make a Spack room, or maybe we'll just follow you in whatever room you're going, like if you were at the real in-person event. And so everybody can join us if they're interested, or they can join a different networking session if they want to chat about something else. So for now, another round of applause for you, and a great engaging the audience, and I look forward to continue chatting with you with these additional questions. So
this meeting is being recorded.
Okay, welcome everybody to SCA's Improving Scientific Software Conference Series 2022. This is the second day afternoon session. My name is Sid Ghosh. I will be your moderator for this afternoon session. This session we have 2 talks and a tutorial. The tutorial is split around the afternoon break, which is between 2:20 and 2:40. And we will be beginning with a talk by Rob Gonzalez-Pita on a GitHub Action self-hosted runner for HPC applications. So Rob is a software engineer employed by the Cooperative Institute for Research in Environmental Science, or known series otherwise, working for NOAA's Global System Laboratory, GSL. So with that, let me hand it over to Rob. Rob, please go ahead.
Thank you, Sid. Good afternoon, everyone. My name is Rob Gonzalez-Pita, and today I'll be speaking about GitHub Actions self-hosted runner for HPC applications. So here's a quick presentation outline. I'll be discussing 3 main topics. First is an overview of the challenges faced in testing our application, which is the rapid refresh forecast system regional workflow. Second, I'll go over continuous integration, GitHub Actions, and self-hosted runners. And third, I'll describe AWS Parallel Cluster as a self-hosted runner. So the RRFS regional workflow is the project we were called to do the continuous integration on. It is one component of the Unified Forecast Systems short-range weather application. The 3 core challenges in testing the regional workflow boil down to the multitude of dependencies, the application complexity, and all of the different forks and branches. So listed here are the majority of dependencies needed for the UFS short-range weather app and regional workflow. As you can see, there are general software stack requirements, as well as application-specific requirements, which we're using HPC Stack for, that need to be installed in order to run the workflow end-to-end. I would like to mention in this slide, I'll go more into our AWS Parallel Cluster self-hosted runner later, but would like to mention here that there's also software shipped with AWS Parallel Cluster. Understanding what software and its version, where it is located, and how to reference or override it need to be accounted for. For example, to leverage the fast interconnects, we used the Intel MPI that ships with AWS Parallel Cluster, as opposed to the Intel One API's Intel MPI. TCL-based modules are pre-installed on parallel clusters, but for our purposes, we needed to use Lua-based modules. So that's to say, the way in which these dependencies were installed on the parallel cluster required some fine-tuning as well, because some of the compute nodes required installation of these dependencies. So next is the app complexity. In order to successfully build the short-range weather app, all of the components need to be compatible, which for the most part is the case, but is not a guarantee. The repositories comprising the UFS short-range weather app are shown. This diagram depicts all of the different repositories that are nested within the application. One of the challenges in setting up the continuous integration tests was keeping up with the active development taking place. We are essentially testing a moving target. There's a perennial need to merge the top of the develop branch for the UFS short-range weather app and regional workflow repositories into our working branches to stay with the current code base. Modifications to scripts, variables, files, etc., in the develop branches needed to be accounted for, and updates were continuously made to automate the running of workflow end-to-end tests tracking the latest code. So go into a little bit of what we're testing. First, we're running a build and compile test of the umbrella application, which verifies the interdependence of these two repositories. When coordinated pull requests to both repositories are submitted, the user fork with the same branch name for both repositories will be tested. As a byproduct of implementing these workflow end-to-end tests as our CI testing framework, we will have automated the process of compilation, running the forecast with all of its associated tasks, including post-processing. So what are the workflow end-to-end tests? Here we're essentially leveraging existing workflow end-to-end tests. These tests include around 75 different workflow configurations with different domains, initial conditions, lateral boundary conditions, and physics suites. These tests in total require a lot of resources, around 2 terabytes of disk and thousands of core hours. Currently running the test suite is a manual process. Here we're testing for completion, not correctness, and end-to-end tests only. We don't have regression or unit tests currently. The workflow end-to-end tests have traditionally been run on a given HPC platform to test the code as well as the system. Part of our work has been to remove machine-specific case statements and provide machine files in moving towards platform agnosticism. So in order to dig a little bit deeper into how we're implementing our continuous integration through GitHub Actions, I'd like to point out the benefits of continuous integration and why it should be a part of every application. My apologies to those of you who are already familiar with CI, but I figured I should mention the benefits. They include increased development cadence, improved communication, higher product quality, increased productivity, risk reduction, an increase in collaboration, incremental changes can be added, and quicker identification of bugs. Diving too much deeper into why continuous integration is a best practice would require a separate presentation, but I'd just like to touch on these points to illustrate how CI pipelines improve the software development process. So there are many tools for implementing continuous integration pipelines. Here are a couple listed. If you don't already have a CI pipeline in place, you're afforded many options. Each has their own benefits and drawbacks. The convenience and accessibility provided by GitHub Actions currently meets our needs. What is a GitHub Actions self-hosted runner? So this is straight from the GitHub documentation. The self-hosted runner is a system that you deploy and manage to execute jobs from GitHub Actions on github.com. Self-hosted runners offer more control over hardware, operating systems, and software tools. They offer more processing power and memory to run larger jobs, and you can install necessary persistent software. These can be virtual, physical, in a container, on premises, or in the cloud. Free to use with GitHub Actions, but you are responsible for the cost of maintaining the runner machine. So why use a GitHub Actions self-hosted runner? A couple of the benefits include the low cost. They're easy to set up on your machine. There's clear pass-fail results, all within the web interface in which your code is already living. It is interactive, so you can drill down into specific failures from the web interface. After making the decision to use GitHub Actions for a CI pipeline, we're afforded the choice of using a GitHub Actions provided runner or a self-hosted runner. So as you can see, the GitHub Actions provided runners are not well suited for HPC applications due to their low core count, memory, and disk space. For an example, running the 70 or so regional workflow end-to-end tests requires significant computational and memory resources, around 2 terabytes of disks and thousands of core hours. This is on top of 5 gigabytes of software stack, 3 gigs of input data, and 47 gigs of fixed files. There are large memory requirements for pre-processing tasks, and a minimum of 6 cores are required for 6 MPI ranks. Ultimately, the reason why we are using a self-hosted runner is due to these data and compute intensive requirements. So in theory, we could use an on-prem self-hosted runner, but the inbound traffic restrictions faced by NOAA HPCs make this an impossibility. So since there are cloud-based services which emulate on-prem HPC environments, why not leverage them? Amazon World Services parallel cluster offering fills the role of the computational environment needed to run our continuous integration tests. A couple bullets here is that its parallel cluster is highly customizable. There's multiple instance types and schedulers. High performance file systems are available, and an elastic fabric adapter for high-speed node connection. Here's an overview of how a GitHub Actions self-hosted runner fits into the pull request process. First, the user creates a PR with additions or modifications to the code base. Code owners are assigned to the repository who have the ability to attach a label to this PR, which initiates the CI pipeline. You can have different events set to trigger workflows, which are defined in the GitHub Actions workflow YAML file. Once the label is applied, the GitHub Actions workflow is initiated, running the workflow end-to-end tests. A series of scripts kick off the job and report its status within the GitHub Actions context. The success or failure of each workflow end-to-end test is reported within the GitHub Actions context, providing all of the code owners and reviewers the ability to view the results. And listed on the right are 2 options that we have of running the workflow end-to-end tests, either as a self-hosted runner as a Docker container or the self-hosted runner as an AWS parallel cluster. Self-hosted runners for GitHub do not have guarantees around running in ephemeral, clean virtual environments and can be persistently compromised by untrusted code in a workflow. That being said, GitHub recommends against using self-hosted runners for public repositories on GitHub. We're currently addressing this issue by having code managers vet each PR before running the CI on the self-hosted runner. And by vet, I don't mean looking through all of the code, but just the individual who submitted the pull request and therefore. By definition, this isn't true continuous integration, as this process is not fully automated. Our continuous integration does require a human intervention step. However, in addressing the possibility of malicious code being executed on the self-hosted runner, our approach mitigates this main security concern. Hopefully you caught Ben Lazarine's presentation yesterday, as he gave a great explanation with examples of the types of shell injection vulnerabilities we are concerned with here. So in the following slides, I'll go over the ease of setting up a self-hosted runner from the GitHub side. Setting up a self-hosted runner from the web interface is very, very easy. There are only 4 clicks required. So from the main repository screen, on the top right, you'll see settings. Click that first. That will bring you to this screen. The second click that you need to make is actions. Third, runners. And then fourth, on the top right, a new self-hosted runner. After you've clicked the new self-hosted runner button, you'll arrive at this screen. From here, you select your runner image. Currently, only Mac OS, Linux, and Windows are supported. Also, not all Linux distributions are supported. So check with the GitHub docs if you're running an atypical operating system. From here, you just copy the commands listed here, execute them on your machine, and you're all set up. Moving on, I'll describe how we've implemented the use of an AWS parallel cluster as a self-hosted runner. Before I get too far into it, I would like to go over the steps of installing parallel cluster and its dependencies, and also how you create a parallel cluster. The majority of the time spent on this project on my end was to appropriately configure the software dependencies on the machine in which to run the CI tests. So that also includes configuring the parallel cluster with the configuration file, as well as SSHing into the cluster and installing the dependencies. So to install AWS Parallel Cluster locally, Python's required, Node, and NVM. The AWS CLI is needed to configure your region, access keys, secret access keys. And once the P cluster and AWS CLI are configured, and you have a key pair, you can create parallel clusters. From this point, it's relatively simple. The P cluster command is used to create, list, stop, update, delete, etc. The parallel clusters. A config file is provided to the P cluster create command. The parallel cluster config file is where you specify all of the AWS specifics, like virtual private cloud, subnets, necessary tags, etc., as well as the cluster specifics. So that would be the instance types, the file system, the scheduler, the shared directory, etc. So once the P cluster create is initiated, you can track its progress from the terminal or on the AWS console. Upon successful creation, an IP address will be provided to SSH into the head node. I would like to mention that spinning up or starting a stopped parallel cluster can also be accomplished from GitHub Actions. There are a couple reasons why we shied away from this approach. One was the time to spin up a cluster and install the dependencies. It takes around 20 minutes to spin up a new parallel cluster, and then roughly 2 hours to install all of our dependencies. This would also be in addition to the 20 minutes it takes to build the short-range weather application. In creating a parallel cluster and installing the dependencies separately, it separates the complexity of setting up the machine in which the tests are run from the actual testing of the application. And thirdly, there's no need to provide AWS access keys within GitHub Actions. So that also eliminates a potential security breach there as well. With the other approach, you would send AWS CLI commands from within the GitHub Actions workflow using GitHub tokens to start an EC2 instance, run the job, and stop the instance. This approach is used for the UFS weather model repository. So while this approach adds significant complexity to the GitHub Actions workflow, it will save on cloud computing costs. Here's a diagram of the AWS parallel cluster infrastructure as it relates to GitHub Actions. First, a user must create a parallel cluster using the pcluster CLI, which is normally done locally. And I briefly described that a couple slides back. Then the arrows move you to the right and up a little bit to the CloudFormation template. AWS CloudFormation is the core service used by AWS Parallel Cluster. Each cluster is represented as a stack, and all the resources required by the cluster are defined within the AWS Parallel Cluster CloudFormation template. However, this CloudFormation template is for the most part abstracted, and a parallel cluster configuration file is used to specify resources. There is a parameter to provide your own CloudFormation template file if you need to customize the default CloudFormation template. So the resources that I mentioned are everything within the white box to the right of the CloudFormation template. Next, the head node, which is a much cheaper instance than the compute nodes on the parallel cluster, must be configured as a self-hosted runner in addition to installing all of the software dependencies. So once configured as a self-hosted runner, it will listen for workflows from GitHub Actions. When the CI is kicked off, by either from applying a label to a pull request or manually, or whichever event you have your workflow set to, on the parallel cluster side of things, Slurm is used to schedule jobs for our tests, and the AWS Elastic Fabric adapter provides fast interconnects for compute nodes. We are storing our UFS data in an S3 bucket, which is the mount point for the Lustre file system on each cluster creation. The ability for new parallel clusters to mount a persistent file system is available, as well as the ability to automatically update the file system from the S3 bucket used as the mount point. We have also split up the two distinct GitHub Actions steps into two separate workflows. Earlier this morning, George McCabe's presentation provided an excellent description with visuals on how the GitHub Actions workflow files are configured, as well as the GitHub Actions interface. Here are a couple of screenshots of our two workflow runs. On the left, in the first workflow, the short-range weather application is built. Sorry if the text is small here and you can't read it, but we essentially clone the RRFS CI repository, clean up the previous short-range weather app build, so remove all of those, check out the short-range weather app, and then build the short-range weather app. The GitHub Actions workflow, which runs the workflow end-to-end tests, only runs if a successful build on the short-range weather app was accomplished. This isolates the two processes and modularizes the workflows for potential ease of refactoring. So you can see in the second workflow, there's an exit on build failure, which will automatically, it won't start if the short-range weather app fails to build. Then we set up the Python environment, list the tests, delete the old tests that are there, and then we have a wrapper script which executes the running of each workflow end-to-end tests as part of the job matrix, where each GitHub action job corresponds to a separate test. This allows for quick and easy troubleshooting as to which tests passed and which tests failed. You can drill down into any of the run test jobs listed in the end-to-end test workflow shown above to see the terminal output of executed commands on the self-hosted runner. So there's a couple of alternative approaches for continuous integration that we're implementing as part of our CI project. One of them is setting up a Docker container complete with Slurm to execute the workflow end-to-end tests. This is a visual of what that infrastructure looks like. A Slurm cluster is created using Docker Compose, which will later migrate to Kubernetes. One container serves as the Slurm master. Another container handles the Slurm front end, where code is cloned, built, and workflows are initiated. Several instances of a third container serve as the Slurm compute nodes. This allows us to test Slurm-based workflows without using parallel cluster. As the third prong of our CI project, we have created the ability to pull the GitHub API with a series of Python scripts from NOAA HPCS for a label attached to a pull request. If a particular label is assigned to a pull request, the workflow end-to-end test suite will run on-prem, and upon completion, comment directly to that PR with the workflow completion status. So in summary, I would like to say a byproduct of using AWS Parallel Cluster as our CI is that we're providing an example and the functionality for a user who might not have access to a NOAA HPC supported platform to run this application on AWS. In summary, the complexity of the UFS and AWS Parallel Cluster pose significant challenges to CI. GitHub Actions self-hosted runners provide a low-cost, easy-to-implement continuous integration capabilities with an intuitive and informative user interface. Using AWS Parallel Cluster appears to be a viable solution for our CI pipeline, in addition to on-prem and Docker approaches. And our next steps include streamlining the provisioning of AWS parallel clusters with all the necessary dependencies, providing updates to GitHub Actions workflows and self-hosted runners when modifications are made to scripts, modules, dependencies, versions, etc. in the repository, which may alter how workflow end-to-end tests are configured and executed. Plans to refactor test infrastructure. So here we'd like to simplify our tests, add unit tests, and only run the workflow end-to-end tests when necessary. That's all that I have today. Thank you for your time and attention. I'd also like to thank my collaborators on this project, Christina Holt, Vanita Haggerty, Chris Harrop, as well as the Improving Scientific Software conference organizers. Thank you.
Thank you, Rob. This is a very interesting talk. If there is any question, please feel free to ask your question in the chat window. Okay, here's a question from Eric. Can you define on-prem again?
Yeah, on-prem stands for on-premises. So that's kind of the distinction between the cloud resources and you know, what you would see in a normal high performance computing you know, cluster, like the actual physical hardware.
Okay, there are no more questions. I have just a simple question. So when you say test for completion, not correctness, presumably you are just testing the scripts infrastructure, that's not the model itself. That's what you mean?
Yeah, exactly. So we're testing all of the scripts running end to end and the whole workflow, as opposed to the scientific accuracy of the model.
Forecast. Okay. And you also mentioned the cluster many times, and at one point the 6 core something like required for your testing. So how many nodes in AWS?
In AWS, we have it, you can specify how many you want, but anywhere from, you know, 20 to 100, you can, I believe you can even go more than that.
Yeah, specifically, I was asking how many do you need typically for your particular workflow?
I believe we run around 40. Each machine that the regional workflow runs on currently has a different number, but between, I think it's 32 for some machines, 40 for others.
Thank you so much. Thank you, Rob. Okay, so let's move on to the second, actually this is a tutorial. The tutorial will be done by Vasiliadis. I'm sorry, did not pronounce it right.
No, that's good.
Yeah. The topic of this tutorial is scalable automation of data management tasks. And you are doing it along with, Vas is a chief customer officer for Globus, which is developed and operated by the University of Chicago. Yeah, so with that, let me hand it over to you, Vas. So do you need any breakout rooms and things like that?
I don't need breakout rooms, but I noticed that the Q&A is via Slido. Is it possible to people to just unmute and ask questions? Because that, I mean, we're going to have some hands-on exercises, and it would be
sure that would
yeah.
be just fine.
Oh, okay.
Fine, Vas.
Yeah, I mean, I encourage people to just interrupt me in the middle of my high-speed flow. And just to make this a little more interactive. So I've got some exercises lined up. Let me Let me share screen here, make sure I can share. So can you see
we can.
slides there? Okay. Actually, I'm going to put these, sorry, I'm going to unshare and put these in the, where should I put them? In the chat. There's some links here for those that do want to follow along. I'm going to be using some Jupyter notebooks and deploying some code, and I've got instances if people want to follow along. I don't know if those, yeah, so there's 3 links there. You're also just more than welcome to sit back and enjoy or check email. Okay, so as Sid said, the focus of this talk is on scaling data management, and this is I proposed this as a follow-on to the presentation I did at this conference last year, which was motivated by the growth in instrument science, and I'll do a little sort of recap of that just to sort of set the overall context again, and then I'm going to talk about automating data at scale, both from the perspective of how we do things that relate, that tie compute and data management together, as well as human in the loop, sort of end-to-end research flows, and then focus on a couple of things in particular. One, which is making data more findable and accessible. That's the F&A in fair data, as many of you are probably well aware. And I'll use an example from the modern research data portal design pattern, which is how to deploy portals as a means to make data more easily accessible, findable, and reusable, and actually have an example of how you can deploy one of those actually with real working code against a real pretty large scale index, and it's something you're welcome to. As I said, you can follow along with me. I'll have instances for everyone if you want to, and it's something you could use as a starting point for your own web app or Science Gateway or portal or so on. Okay, so without further ado, and if my dog will cooperate, I apologize for the background noise. So this was the way I set things up last time, and I'll just do it again in summary form. Lots of instruments, lots of data, and the big thing that's driving this and making automation really a requirement as rather than an optional is a chart like this, right? The brightness is increasing, as you can see, orders of magnitude faster than even Moore's law and other curves that we've seen starting to see taper off. And as a result, what that translates to really is a lot more data, much higher data velocity. And so when you're having to deal with these experiments that are running in some cases 24/7 around light sources, as well as instruments that are satellites and things that are capturing data continuously, it's pretty clear that these are not data problems that can be solved by sort of ad hoc and clicking on things, and sometimes you could script some things, but generally the scale, the complexity is such that you need something more. So I'm going to hopefully give you some food for thought on how we sort of address that. And for most of these scenarios that we work with researchers on, there seems to be this fairly common pattern that repeats over and over. So at the start of the process, you've got some kind of instrument, typically something that's imaging something, be it cryo-EM or bright X-ray of some kind, or a satellite or what have you. It's grabbing images, it's capturing them typically to some device that's stored, that's attached to sort of right there. That device typically doesn't have much capacity, so there's an immediate need to pull the data off there to some other storage. Typically, there's some computation that needs to happen, whether it be image recomposition or rendering of 3D images or functional video, things like that. All of that very computationally intensive. So this is typically happening elsewhere, and then some of those data products or the results of those analyses get pushed out and typically need some description in the form of metadata, sometimes persistent identities, persistent IDs, and then really becomes a challenge to reuse those and take full advantage of them unless you have some means to search for them and discover them. So we're starting to see a lot more folks putting up some type of data portal or science gateway that on the back end of this flow, things are there and searchable and more easily findable. And as one of my colleagues says, then science just happens, right? So that's all it takes. So I probably should have asked for a show of hands, but I can't see the audience now that I'm sharing. So I imagine maybe some people are familiar with Globus, perhaps mostly just as a way to move data around. Certainly within NCAR, UCAR, more broadly, we've got one of our oldest installed base. So hopefully you've used that service for that. But mostly what I want to talk about today are in part that transfer piece, but that's not really central to this. It's more about some of the things that we do around scaling the data through some of the services we have in the platform. So some of it's available via the same web interface, but a lot of it is much more programmatically controlled, which is what you need to do, as I said earlier, at scale. Skip that. So when we talk about automation, we really think about it in terms of a sort of a progression, if you will. So on the top left here, you've got the timer service. So that's a very narrowly focused thing for scheduling and automating data movement. The next step in the progression is the command line tools that we make available that allow you to control most of the services programmatically through scripts, and also allow you to integrate some of those scripts into other bigger scripts or other infrastructure. And then it's sort of at the end of the continuum is this relatively new service called Flows. We've been talking about it for a while, but it's really come to fruition now within the last year or so, which is really being able to very robustly and scalably run these long-running flows with different types of steps in them, both compute and data related, as well as human in the loop, and be able to do that reliably, which is really tricky, especially for some of these research flows that may run for hours or days. So I'll touch on each of these briefly, the first couple rather, and then I'll spend more time on the flows because that's really where it's at right now. So firstly, the timer service. There's a few use cases where you need to replicate data periodically. It's sort of a more regular schedule. I know of some facilities where the sort of windows of sort of maintenance or accessibility for the data on the instrument where the instrument's out of service, and so and I think that's true in some satellite applications as well. So you've got these windows of time where you have X hours or whatever it is, minutes, some cases, to pull whatever's off the instrument at that point. So that's a perfect example of where using something like the timer service makes sense. So a lot of people talk about it as Globus cron. In fact, the NIH is using it very extensively. Even calls it that on their website. So the idea here is that you can schedule a transfer and have it run repeatedly on a schedule. I'm actually going to pop over into just show you some of this so it makes it a little more real. So if I go into the Globus, I'm just going to use the web app for now. And please, someone just yell if this is too small. So instead of pointing and clicking to run a transfer, so if I were to run something from, I don't know, pull the TerraFusion data set, oops, that wasn't a good one, to some, let's say I want to remove, I don't know, some data set from one place to another on a repeated basis. I can go down here, I can set the options if I want to sync files, etc. And then I can say, all right, I'm going to run this, starting whatever at 3 a.m. and etc. So this is the scheduling, and you can repeat this, as I said, on every day, every end days and end dates. So pretty much like the calendar scheduling, we're pretty familiar with that. So that's, useful for certain use cases. It's very powerful, actually. You can drive the same process through a command line tool. So you can create these timers and have them execute. You get notified when they run, you get notified when they complete, and so on. So that's, scheduled transfers, pretty easy. If you want to go a little broader than that, beyond just transfer, then the command line is actually a good place to go. So the command line actually exposes a lot more options in many cases than even the web application. So you've got more options to control things at a more fine-grained level. And beyond transfer, you can do things like share data, sort of, manage access controls for shared data sets. You can manage group membership so people can get access or have access revoked on certain data. You can invoke search, which we'll talk about a lot more, especially after the break. So all of that is available through the command line. And as I said, really handy if you want to, add it to your existing script, so you can call out and, stage in data before you run a job or what have you, pull data down and run an ingest into an index with metadata, those kinds of things, all very, very easily done through the command line tools. And so, as I said, at the end of that sort of progression is this service called Globus Flows. And the idea here is that you have the ability to define some series of steps or actions, as we call them, and you can create this definition. It's essentially a state machine is what it is, and you define it and you register it with a Globus service, and then users, your users get to go and run it on demand, or it can be triggered based on certain events occurring. The trigger service is something that's a little newer. We don't have it generally available just yet, but it's in use at some of the DOE labs right now. So the flow defines the series of actions, and each action can be related to some kind of data task, or it can be related to some kind of compute task, or something else. So it could even be a human in the loop who has to review something and allow things to progress to the next step. We have that in some imaging use cases where alignment of samples or things like that is very precise, and if things are a little off, then the images are useless. So they will do a run of a small number of samples and then make sure the alignment or the focusing is appropriate, and the user will sort of approve, and then the flow can continue and run things at scale. So all those kinds of actions are possible for many of them. We have pre-built these things that are called action providers. So that's, if you will, you think about that as the interface to the service or the system that you need to access and act on. So for things for services within the Globus ecosystem, like file transfer, like file sharing, like indexing and searching, etc. There's providers for all of that, but it's also an extensible model such that you can build your own action providers for your own custom applications and have those be part of these longer, sort of more complex, longer running flows. So as I said, this is essentially a state machine, and we actually use Amazon step functions at its core. So what we've done is taken step functions, wrapped it with primarily some of the authorization access control mechanisms that are built into the Globus platform, which I'll talk briefly about a little bit later on, and provided an API that makes this consumable in the same consistent way as all the other Globus services. So, and the fact that it's backed by a service like step functions hopefully suggests its reliability and its robustness at scale. And certainly we haven't run into any issues on that side of the house. That's for sure. Excuse me. As I said, these are some of the action providers that we have available. So if you want to run any of these tasks, set an access control rule or mint a persistent identifier for a data set or ingest data into an index, etc. All of those are available. And then there's a few that this is a short list. There's actually more than these available of people that build these custom action providers as part of their flows. And so we have a toolkit that you can use for that. And the idea here is to create this extensible ecosystem that allows people to have this composable architecture of different actions with different action providers based on their needs. So the ecosystem as a whole, and so as far as thinking about the life cycle of these flows, there's the definition and deployment of the flow. That's typically more of an administrative or developer / DevOps sort of function. And because there's a little bit of technical craft in there that you have to deal with. The more technical thing arguably is actually if you have to write your own action providers, because that does require that you build, you actually essentially expose an API that can be called to do things like run the action, check status of the action, cancel the action, and so on. So in some cases where you already have an API, that's actually trivial. In other cases, if you're talking to some legacy systems, that actually might be a little more work. But then from the perspective of the scientists and the end users, it's very trivial to just go and point and click and run the flows. Once it's been fully configured, they just provide input values and just have it go. So it's very easy to scale that way. And as I said, the more interesting use case is having these flows triggered programmatically by events on a file system, perhaps, or things coming off a microscope, what have you. Okay, so let's we pause there enough of the slides, and let's actually walk through one of these flows, or just get a sense for what this looks like. We have this Jupyter hub set up at this address. You can see it here, jupyter.demo.globus.org. I'll put it in the chat, jupyter.demo. So, oops. Typo there. Okay, so if you want to follow along, oops, and that's spelled incorrectly. That's what happens when you don't copy paste. It's Jupyter. Anyway, I will go to that hub. You're welcome to join me there, and let me pull it up here. I actually just did another one of these tutorials at another conference. It's ended about half an hour ago, so I'm still logged in here and going. So when you access that for the first time, it'll ask you to log in. Again, if you've logged in to Globus, if you use Globus, it's pretty straightforward. But if you haven't, the login, there's many login options. You can access it with a Google account or with your UCAR account. It's through our federated login. Should be pretty straightforward, and you can go into the hub, and on your server you'll see this notebooks directory, and the notebook that I'm going to focus on is this one here, automation using Globus flows. So I'll open that up. And I'll talk about a few things. So what this notebook is, a very, obviously it's just it's an educational tool as much as anything, mostly to allow you to see some of the key concepts here. So this flow is not by any means a challenging one, but it's actually something that's fairly common and very nice to automate, because if you're dealing with lots and lots of data, it's great to have even something so simple. So this is really the flow, which is you get some data somewhere. This is typically, if data is coming out of some analysis system, you want to put it in some storage area, some tier of storage where it's more broadly accessible or available to the rest of the project team, perhaps, or perhaps the community. And so you want to set appropriate access rules to say which people or which groups of people can access that data. So this is something that is just two actions in this flow. One is move the data, and the other one is set the appropriate permissions. And so I'm going to use some simple files and things on endpoints that I want. It doesn't serve the purpose here to go into that in detail. Before we use any of these services, these are all controlled through secured APIs. So you have to make authenticated calls to the Globus service APIs. So the first thing we do is get access tokens from Globus Auth, which is the service that underpins everything. I'll cover that in a bit more detail later on, but I wanted to show you this so you have some context when I start talking about the more detailed technical bits. So in this case, this Jupyter Hub is registered as a client application with Globus Auth. So when you log into it, it gets the appropriate access tokens with the appropriate scopes from Globus. It puts them in the database, and then I can retrieve them and use them to access other services as me. So, so if I run that that step, I actually print out all the various access tokens that I get back. So this access token here will allow me to talk to Fair Research and get a Mundt persistent identifier. This token is if I want to talk to the search service and create or update a search index, and so on. And the one we care about here in particular is this one, the flows service. So this gives me access to do various things on flows. So I have my credentials in hand. Now I can start talking to the service. So the first thing I'm going to do is define the flow. As I said, there's two steps to this flow. I don't know if the text is maybe too small. I'm going to make it a little smaller. Whoops, wrong way. So it can all fit on one page. So that's the flow there. You can see it's basically the state machine that says there are two states. The one is move files, and the other one is set permission. And the flow starts at move files. So it moves files from a source endpoint to a destination endpoint and the corresponding paths. And it waits up to 60 minutes in this case for completion. This is this probably wouldn't work if it was a really massive data set, but just for the purposes of demonstration. So once it completes, then the next step is to set the permissions. And so here we say, we specify in this flow which endpoint the data is going to live on and the path, what permissions we want to grant, read-only access by default or read-write, and who we want to grant the access to. So this can be a group or an individual user, and it can also be another application. So as I said, this Jupyter Hub is registered as a client application in Globus. As of many others, we actually have some tens of thousands of client app registrations out there. So if you have an application, it has its own identity, just like an individual, and the app can use that to get the appropriate tokens if it has permissions to do so, and act on its own behalf to invoke Globus services or other external services using those credentials. So anyway, here we set the permission in this case to a group. I think we'll show the data in a bit. So that's the definition of the flow, and then corresponding to that is a definition of the inputs that are going to go that are required by the flow. So we saw there that we have the source and destination endpoints and paths, and then the principal type is the type of entity that we're sharing with. And so we're gonna, let me just clear that space so you can all see it. So that's the input schema. And so I've defined these manually here, but we also have tooling that will allow you to simply say the steps that you want to do, and it will generate the flows and the schemas and all of that stuff automatically. And then you can just run the deploy command and have all that pushed out to the Globus Flow service. So here, just walking through it a little more manually so you can see what's sort of behind the scenes. So we've got the flow defined, and now we're going to push it in. So I'm going to change the name here so we can easily identify it. We'll call this ISS tutorial flow. And I don't need the UUID on the end of that. That just makes it ugly. I usually do that if a lot of people are running tutorials. Maybe make it this year's one. Okay, it's still around next year. How's that? So I'm going to pass the flow definition we just created above and the input schema and that title, and that's it. So hit return. So the flow has been deployed. So this flow is just another resource in the Globus platform. It has its own UUID, and that's how I invoke it. That's how I refer to it if I want to update it, do whatever. And a very important part is this thing called the scope. So this is what Globus requires a user of this to consent to. This has the consents. Oops. When the user tries to run this, it will attempt to get, sorry, let me just make it the right size again. It will attempt to get the user's consent to access whatever it is, to access, in this case, this flow. So every flow has its own scope. And when you're running it, you have to consent to agree to do what the flow wants to do on your behalf. So I'm just going to get my identity. This is now just making a quick call out to the auth service and getting user information, mostly because I want to use my identity ID just to create a unique location. Again, this is just for convenience because we're running multiple of these in parallel sometimes. So So I'm defining the inputs, as you saw above, source endpoint, destination endpoint, and then in this case, I'm sharing with this group called My Collaborators, which happens to be the tutorial users group. So that's something that you can actually join right now if you like, if you're online and following along. If you're not a member of the tutorial group, you can join that. And then any data that I share through this will be available to you by virtue of your membership in that group. And down here, if we wanted to just share with an individual instead, or a client application, equally importantly, we could just put their identity ID in here instead of the group ID. So I'll set the input values, and now we're going to authorize it. So now, as I said, the flow service created a new scope. So we need to essentially update our credentials. We need to get an access token that includes that scope, because when we try and run it, Globus is going to say, do you have permission to run this thing? So that's really what we're doing here. So we have to just pop out and authenticate. So this is just for informational purposes. So what it's saying is, do you consent to having this client application start and manage runs for this flow? Yes, obviously I want to run it. So I'll get my code back and go paste it in here. Now this is something that I only have to do once it's authorized, and I can run it multiple times. This is not something that has to happen every time. Okay. So now we run the flow. Okay, so what we're doing here is we're giving it a unique label so that I can identify it, because there's potentially thousands of flows floating around there that might be visible to me. So I'm just going to do run at ISS tutorial for me. So we do this by calling the run flow method, and we provided that scope that was given to us. And as well some other information here, the inputs, and then of course the ID of the flow that was created way up here when we deployed it. So that's the flow ID there. So we're going to run that, and then what we're going to do is basically, it's kind of brute force includes you, but we're just going to sit in the little wait loop until we're going to poll it, check every 5 seconds. If it's still active, if something goes wrong, it'll error out and it'll tell us what happened. This one should hopefully not fail. It's pretty straightforward. It's just doing a move of a couple files and then setting permissions. So most of the overhead here there's not much real work to do. Most of the overhead is going between this and the Globus service and the Amazon step functions. Some of the housekeeping. But the point is, as simple as this is, if you sort of imagine a multi-step thing. In fact, some of the flows I've seen are like 11 or 12 steps, that long-running computations in the middle, etc. Imagine those running on order, millions of instances of data, files, runs, what have you. That's the sort of scale that we're talking about. Although realistically, most people are only running maybe order hundreds of these, so relatively easy to handle that. But if you do need to scale even orders of magnitude above that, the capabilities are there. Okay, so this flow is taking extraordinarily long today. So something went wrong. Okay, spoke too soon. Timeout on state file. So I must have probably given it a bad. Yes. Okay, this system is no longer available. This is a old storage system, so could run this on a different. Should run it on a different endpoint. But anyway, the point is, we do that. So once the data was there, I could actually go and look at it, and then because permissions were given to me, and then I could get rid of the permissions. But since it doesn't move, there's no point doing that. So that's, I just wanted to show that to you so that you're aware and know at least some of the machinery that comes together to make this work. What I do want to show you as well here is to switch over to the web app, and you can see some of these flows from the user's perspective. So all that cruft is there, it's hidden behind here. As a user, this is what I would see. I would see, you know, a library of flows that either I have created or have been created, and I have been given access to either view or run. So these are viewable, but I can't run them. There's no start button. But here is one that I could run. Here's an interesting one. This is an 11-step flow. So this is actually a flow from one of the, oops, what happened there? One of the beam lines at the advanced photon source. So the XPCS project. So they get images and then they run some massive compute jobs on GPU cluster, and then do all sorts of other things and eventually publish it. And it's all fully automated. So that's a pretty interesting one. So if I were to do this sort of ad hoc, I could just click here, start it, it would run. I could monitor it by going to the runs page. I could go in here and look and see, you know, the event log, what went wrong, what worked, what didn't, etc., all the values. So it's like a full audit trail as well, as a status check. And there's our failed one. Okay, let me pause there and see if there are any questions. Excuse me, a little frog in my throat here. Feel free to unmute. Anything?
Yeah, I just posted the link, so that's
not. Oh, just for the links. Okay. Yeah. Okay. Whoops. Sorry. For some reason it keeps taking.
So while others are warming up, can I ask? It's a dumb question here. Our users, because we do support the supercomputing users here at Sizzle. So yeah. Our users, many of them ask for access to cron tabs. Yeah. So do I get it right that I can schedule tasks using your Globus flow?
Yeah.
Doing certain thing?
Yeah, you can absolutely do that. Yes. Yeah. So you can schedule a flow to run. If it's just a transfer, you can use the timer service, but you can have one of the things that the flow can do is wait as well. So you can have, you know, arbitrarily sort of structured things based on what your requirements are. Yeah.
And it can be triggered also based on certain events, right?
Yeah, it can. As I said, that service, the trigger service, is in an early release stage. It's being used, I think, on one or two of the beam lines in Argonne, but we haven't made that generally available. But that will be coming sometime in the course of the year. Yeah.
Specifically, I asked because of the reason when many of our users do what you call field campaign, where the observational data from various weather station, when it is ready, they will pull it up, and then based on that, they will do the predictions. So.
Yeah, exactly. And if that's so it can be triggered by some files showing up, or if it's something that happens within specified windows, that's even easier because then you can have it scheduled. Yeah.
Thank you.
Sure. Any other questions? Okay.
There's a question in Slido.
Oh, I don't know if I can. Where is that? Let me see. I have so many windows open. Okay. There was an endpoint invalid. Move windows. Is there a replacement? Yeah. So there is a replacement. Yeah, let me actually do that. We have, what time is it? Okay. There is a new, gosh, I don't know why this smiley keyboard is popping up here all the time. There is a new, there's a replacement system for that petrol. It was this one here, the petrol test bed that's basically been retired. The new system is called Eagle, and I just have to get, we have actually set up tutorial endpoints on that. So it's this one here. So,
can you reshare your screen?
Oh, I'm sorry. I didn't realize that. Sorry about that. Yes. Oh, I have to stop the other sharing. Let me just read the other question. Is there a way to authenticate a flow without having to go through a browser? You can, so that initial authentication is when you deploy it. And it does require, well, it either requires you to authenticate or the application can be the user, but it doesn't need to be authenticated. So yeah, it doesn't necessarily have to go through a browser, but it has to be authenticated. And I see, sorry, just while I'm here, are there controls for limiting for how long a flow is authenticated to work? You can set for every step in the flow timeouts, basically deadlines, and I think also for the overall flow. I'm not 100% sure, but I think so. But as far as the authentication, those access tokens are short-lived. I forget what the default is, but I believe that's also configurable. Okay, sharing. Oh, stop that sharing. Sorry. Okay. So you can see my Eagle endpoint page, hopefully. So this is actually the UUID. This notebook hasn't been updated in the hub yet. This is endpoint just recently came online. So I don't know if this will, whoops. Don't know if this will necessarily work because I'm not sure if the paths are probably not the same, but we could always just run through it. Let's just see if that actually runs while we're about it. So that may work. I'm not sure. I think the paths are different, so that will probably also fail. But I will. I'll pay attention to that right after. I hadn't realized that we still had that. This is pulling from a repo that hasn't been updated yet. So, oops. Okay, so that I think succeeded. Yeah, so that worked. Yeah, so this is the status you'll get. Flow succeeded, and then we should be able to go and look at that data. So whatever files were moved there, I can go click on them, and it'll drop me into Globus endpoint that was created right there temporarily on that endpoint, or the folder was created there. Yeah. So what actually happened there was that directory with those files in it was everyone who's a member of the tutorial group was granted access on that folder. And in fact, just to sort of show you how all that fits together, if I go and look at the permissions, I should see that listed there now as a recent addition, right? So this permission was just added there at 3:08 p.m. Central Time here. So so that's what happened there. And now in the next step here, just because we run this a lot, this next piece just cleans all that up. So it removes everything, and then it also removes the access permission. So if I go here and refresh this, that permission should have been revoked. Besides, the data is no longer there either. Yeah, so that's now gone. Okay, so that was, thank you for the catch, whoever that was, appreciate it. If you have other questions, just feel free to speak up directly, because I can't see the Slido one, and I have to keep switching over. The session is until 3:20, and then we break, right? Or 2:20 Mountain. Is that correct, Sid?
Yeah, that's correct.
Okay.
Till 2:20.
Yeah.
But since after the break, also it is your session, make it logical for you, whatever works.
Yeah, sure. No, I mean, I definitely want to give people a break, because I know firsthand how hard it is to sit in front of a Zoom session with this kind of stuff. Okay. Right, so let me jump back to some slides and talk about a couple more things here. Okay, so that's Globus Flow. So I'm going to switch gears. So that was about automating these pieces, but the downstream part of data management, which is making sure you've got robust repositories with good indexes and easily sort of discoverable data sets. That's a pretty big, pretty heavy lift as well. And so some years ago, and some of you may have come across this modern research portal design pattern. It was something that was developed jointly by a couple of folks at the University of Chicago and a group out at Berkeley Labs, the ESNet team. And so you can go to that website and see there's all sorts of materials there. But I'm actually going to skip these slides. So the idea behind this modern research data portal is it's twofold. The one is that you need the right type of infrastructure if you're going to do data management at scale, and it's sort of physical infrastructure. So you can see here in the gray, sort of networking infrastructure that creates a nice clean data path, so you can maximize usage of the bandwidth that you have. And we're all blessed in that we have spectacular amounts of bandwidth, but sometimes we just don't have the right tools to use it or the right setup. And then the other piece of the physical infrastructure is appropriate data transfer nodes. So having dedicated equipment, be they VMs or physical machines or what have you, but as long as they are sort of designed to optimize data flows, that's an important thing. Oops, sorry, just keep skipping ahead here. And then so combine that physical infrastructure with the software side, if you will, which is threefold. The one piece is Globus Connect. I'll talk about that in a second. Then there's all these platform services, but then making all of this usable requires something a little higher order, a little more sort of easier to access and use. And that's where our portal framework comes in. So we have an open source portal framework that's built on Django. So I'll spend a little bit of time talking about that after the break. So the Globus Connect piece, that's the software that's used to make a storage system accessible via Globus. We support obviously any POSIX file compliant file system, but also increasingly a list of object stores and other types of archival systems. And so when sometimes when we talk about this, moving to this design pattern, people will ask, well, why do I even need this? What's wrong with my LRDP, my legacy research data portal? It's not very modern, but it works. And I really like this quote. You might have come across it before. Charles, known as the boss, I think, Charles the Boss Kettering. I think he was a Chrysler GM back in the day. But I think this is a great saying, right? A lot of us, we recognize the pace of evolution in some of the technologies, but certainly when it comes to this type of infrastructure, if you have infrastructure that's 10 plus years old, probably there's lots of room for improvement. And really what you're moving away from, for those that are not familiar with the Science DMZ design pattern, this is the traditional way of deploying data portals, science gateways, web apps for research. You have a web server that has all the sort of domain and business logic in it, the search, the databases, authentication, and then you have the data, the storage system somehow accessible to that, and they all sit behind these devices like stateful packet inspection devices and other things that really are not that performant. That some of them are, but the bigger issue also is that you're on the same network path as all the other traffic, which includes, who knows, right? On some, I work at a university campus, as probably many of you. The student video streaming probably takes up most of our bandwidth. So, you don't want to be competing with that. And so the idea is that you create this Science DMZ that essentially carves out a nice clean data path, sort of allowing you to take full advantage of the fat pipes that we have at our disposal. I think a lot of places now are sort of 100 gig to multiple of their collaborating institutions. So, excuse me, no reason why we should be constraining ourselves and having everything go through this thin straw. But even in this architecture, you'll see that the core application itself is still sitting behind the firewall because it actually can benefit from some of the additional controls, and also the fact that this is very low traffic volume, certainly as compared with the data that's flowing over the green path. So once you have that in place, then you can deploy a nice portal with high-speed data movement. And this is one that we like to show a lot. We jointly developed this with the Argonne Leadership Computing Facility, but they came up with a cool name of ACDC, which stands for the LCF Community Data Co-op. So this is, I think, a really a true exemplar of what I was referring to when I said, having something at a higher level that brings it all together and makes the data accessible. So here we have actually a collection of portals that many of them are actually tied to the advanced photon source. So you can see X-ray imaging, X-ray photon correlation. But this one is a different one. This is a curated set of materials data for materials characterization. This one is yet a different thing. It's around DL Hub, stands for Deep Learning Hub. So it's about machine learning models and deploying models, discovering models and running DL models. So, oops, gosh, excuse me. So if we click on one of these, and these are all separate, and you can see some of them had different access controls. There's some said private or public, but this is a public accessible one. So this has almost 1 million records in the data set. And the nice thing is you've got this faceted search that allows you to poke around the data. And then when you find the thing you want, you can just go and get the data. Excuse me, to get some water here shortly. So having this kind of interface in front of these large data stores certainly makes it findable, makes data more findable, more accessible. But it's really important to put it there because of the scale of data, because there really are very few better ways to get the data accessible. In fact, this one goes a step further by even suggesting related data sets using some machine learning algorithms as well. So lots of interesting things you can do with these portals. This one is particularly sort of sophisticated in that sense. We're going to take a break because I think we're right at time. When we come back, I'm actually going to show you the framework that was used for this, and I'll actually walk through an exercise where you can even deploy it and run one of these yourselves, literally in like 10 or 15 minutes. So we'll break there. Sid, how much time do we have for the break?
Yeah, till 2:40. That is 20 minutes.
20 minutes. Okay, great.
Yeah.
Okay. Thank you. We'll see you back at 2:40.
2:40 Mountain. Thank you.
So do you want to wait a couple of minutes, or should we just get started?
I'd say give folks a couple of minutes.
Okay.
Since your session is up to 3:40, I guess you will have a little more time and a little more flexibility. I mean, yeah.
Yeah, there's going to be a lot of hands-on stuff here. So if people are not following along, we might get done sooner, but I'm hoping that people will find it informative.
Vas, you'll have to swap displays. We're seeing your presenter view right now.
Ah, that's odd.
There you go. Perfect.
Okay. Actually, you know what I'm going to do? Let me change this around, because it's weird, because I want to be able to work on the big screen when I do the demos. 1 second, sorry.
Okay, Wes, I think you can go ahead.
Okay. Let's see. So that one. Are you seeing the flows page right now?
Yes, we are.
Yes.
Okay. All right. So then, in theory, this should also show up there, right? You're seeing slides now, I assume. Okay. So I just walked through, just showed you briefly that that one example of this large-scale portal with this very diverse set of data. That is built using a combination of some of these platform services and is also underpinned by that MRDP, the sort of the physical infrastructure of the MRDP design pattern. So there's a very well-architected set of data transfer nodes that are dedicated in Science DMZ on a 100 gig link, and scientists are loving that and have been for the last couple of years when that's been in place. So I just want to highlight a couple of these services. I'm not going to dive into them. We don't have the time, but mostly want to make you aware of the role each of these play, and then we'll get into a hands-on exercise again, so you can actually see how relatively easy it is to stand up one of these things. So underpinning everything is this service called Globus Auth, which is the thing that brokers the access control, authentication, authorization, not just between a user who's trying to access global services, but equally between different applications that are talking to each other, as well as different devices that are talking to applications. So it's something that we've built as something that's extensible. It is essentially the OAuth 2 standard. So if you're familiar with OAuth 2 and OIDC OpenID Connect, then you know well what I'm talking about. If you're not, suffice it to say, this is really the standard for web-based authentication authorization. It's adopted pretty much universally, and we started moving down this path about 7 or 8 years ago. So we sort of got most of the pieces figured out. It's pretty complex stuff, but we've actually tried to sort of shield users from a lot of these complexities. But this is also what makes it very powerful and allows us to do interesting things like some of the stuff I'll talk about on the search side in a bit. So the auth service allows the application, the portal in this case, to access things and do things on your behalf as a user who's authenticated, but it also can act of its own accord. So it has its own identity. I like to joke that apps are people too, not app, but apps. So when you create the portal, you register it with GlobalSoft. We'll do that in a second here. You get a client ID. That client ID is actually, that UUID is akin to sort of the equivalent of the user's identity, my identity, Vasiliadis, Chicago. So this thing has a UUID at apps.globus.auth.org, etc. So that's an important piece, is the authentication. Transfer and sharing is kind of core to everything here that we do. The one important thing in the context of making data more broadly accessible is the need to use these things called guest collections. So for those not familiar with Globus, we have two ways of accessing data. One is through what we call a mapped collection, which is where you map the person logged into Globus, the Globus identity, you map it to a local user that has access to that storage system, to that data. So that's typical if you have your users in your accessing your HPC cluster or whatever. They have local accounts that they log in with. You map the Globus identity to that local account. But when you want to go outside the organization, and especially if you want to go to sort of community-wide and share reference data, stuff like that, that's where you need a different mechanism, because you can't be creating local or temporary accounts. So that's where the guest collections come in, which allow the application, or the user and the application, to set permissions, access permissions on data without requiring that they be mapped to a local account. So it's all done sort of with this overlay set of permissions that's managed in the Globus service. And this is a very widely used mechanism now. In fact, some groups like the NIH have literally thousands and thousands of these guest collections for all their projects and PIs. So that's another piece of sort of software infrastructure that's important. Let's skip that. So I'm going to go into a hands-on exercise here, and you're encouraged, more than welcome, definitely encouraged to follow along. I put the two links again in the chat in case people went on when we started this. So I've got some virtual machines running some EC2 instances. So what I'm going to do is I'm going to go to a command line, and actually before we do that, I'm going to do something else. Before you deploy an application, the first thing you need to do is, I mentioned this term registering. I mentioned it a couple of times, I think, in passing in the first half. But the idea here is that in order to access Globus Auth and to access the services through Globus Auth, you need to be registered. That the auth needs to know who the application is, that it exists. And the application needs to present credentials because, as I said, all these APIs, all these services are protected and they require authenticated calls. So the way we do this is by registering on this website here, developers.globus.org. So this is what I'm gonna do first before, whoops. Sorry, the screens are not cooperating right now. I'm going to put this here. And then I'm going to go to that website on the side here. How to make it all fit on one page. So we're going to deploy this portal. We have to tell Globus Auth about it so that it can issue the appropriate credentials when users access it and grant them the right sets of permissions. So I'm going to go to developers.globus.org. You'll see that page. If you have not done this before, when you log in, you click here to register your app, and you'll be prompted to create a project. That's just an organizing construct. It doesn't serve any sort of real purpose other than to keep things manageable. I have a bunch of these. So what you do is you add a new application. So we will call this one ISS portal. And this is really the only important piece of information you need to provide Globus Auth, which is this thing called the redirect URL, or a set of redirect URLs. I have them here in the slides. If you want, I can post these also in the chat. Let me do that in case people are following along. So you replace the N with the number of your instance. So if you claimed an instance on that spreadsheet link, so I'm actually gonna go and claim another one down here. So I'm gonna claim 15. Okay, so mine's gonna be 15. Okay, and what this URL is, what these URLs are, it's an endpoint in your application that the flow will be redirected to once the user has authenticated and gotten a credential. So what will happen is if it's a user logging in, they'll be redirected to log in with whatever identity. So it's a UCAR, or it's maybe they use their ORCID or whatever. When they come back from that identity provider as authenticated, they go to Globus Auth, and then Globus Auth says to your application, here is a temporary authorization code for this user that just authenticated that you can exchange for access tokens. And so that redirect back has to go somewhere in the application. So that's what we're specifying here. So I'm going to save that. And that will create this client ID. So I just mentioned that just now about the application being able to act as essentially as a user. So here is this application's identity. It's the client ID at clients.auth.globus.org. So everything I can do as a living, breathing human user, this application can do, well, almost everything. So I'm going to save these now. So this is the client ID, and then there's a corresponding secret. So let me just put this here so that I have it handy. And the secret and the client ID are used in conjunction. It's just like other cryptographic systems. It's a two-part key. So you can think of it as private and public, even though none of these should be public ever. So once I have those, I can now move over and deploy my portal. So I'm going to go to my instance, and we're going to use a local user on the instance called dev, and it's dev and then the number of your instance. So mine is 15. So I'm going to SSH as dev 15 at tutorial15.globus.demo.org. And the password is globus_2022 #. I'll put that in the chat as well. Okay. So, so here I am, and I'm going to deploy something called the Django Globus Portal Framework. So as the name suggests, it's the Django framework, which is a widely used Python web framework, and we chose that because, as they say in the docs, it comes with its batteries included, which means it has a lot of the pieces that are needed to get up and running very quickly. And so we've taken that and we've extended it and integrated it with Globus Auth and added some additional pieces, in particular to enable this searching of large data sets, and made it such that it can be very easily deployed with practically no coding to speak of. But then, of course, it serves as a starting point that you can then build on and extend based on your needs. So, so in this website, in this Git repo that I also shared up above there, 3 or 4 links up, I have a file. So what we've done here, we've done the first step, which is to register the auth client. And now we're going to use the commands here, which is in this file, to deploy. So let me make this a little narrower. All right, so first thing I'm going to do is, because I'm going to keep going to this directory, I'm going to export this thing, call it project slug. That's a web app term. You might have come across that. So I'm just going to call this, I don't know, how about VAS ISS? Doesn't sound very good. Okay. So all this runs in, it's all Python-based code. So I'm going to run it all in the virtual environment. So I'm not polluting everything else. So I'm going to first, it's all been set up on these instances. So you can just, all the packages and dependencies are in place. So you can just activate the port, the virtual environment. And then we use this package called Cookie Cutter, which is a way, as the name suggests, to deploy these applications in a cookie cutter way that's sort of pre-packaged and almost essentially completely pre-configured. So I'm going to run that, and it's going to prompt me for a few things. Don't use spaces. Don't use the default of spaces if you're following along. Actually, just put underscores or dashes. So I'm going to just, I suppose I'll stick with this bizarre name. So this is just the directory structure that's going to be created. So the top level is the project, and then within that we're going to have the first portal. They're just going to be called the same thing. So this is a science gateway, whatever. I'm just going to accept all the other defaults. And this is all open source code, so you can pick the open source license under which you want to make yours available. The only thing I need to pay attention to is down here, Globus client ID. So this is where I'm going to go and copy paste that ID that we just created on developers.globus.org. So that's the ID, and then the corresponding secret. And then the search index. So I haven't talked about search in detail yet, but every index in the Globus search service is uniquely identified by a UUID. So this is a sample one that we have available, so that when you deploy this for the first time, you can actually see some real results and you can get an idea of how everything works. So I'm just going to go ahead and accept that. And now I can go into this directory and run this command. Just there's a couple more things that need to be installed. So this is actually finalizing the installation. That's pulling down the packages from the framework, doing its thing. And there's one piece of configuration before I move everything into place. So I have to edit this file, which is where that's interesting. Where all the settings for the app are stored. So this is what this file looks like. And really, the only thing I need to do is add this line here, Django extensions, this little bit of text to the apps. This is actually something you don't normally have to do. This is I'm doing it here because we're running on these virtual machines, remote servers, and we're running with HTTPS. And Django by default is only designed, what we have here is just a development server. It's not a production deployment. So this is kind of a little bit of a hack to get it to run, sort of properly, like looking like a real app. Normally, you would deploy this somewhat differently if you're putting it into production. So, but in the meantime, I'm just going to do that just for convenience. So, having changed that, I can do this migration, which is basically creating the database where it will store settings and it will store user profiles, etc. And then the step just puts all the static files somewhere where they can be served better. So now we're ready to run. And I can go here and just run it. And now I can go and view this portal. And I will go to HTTPS at tut15.glovisdemo.org. And it's port 8443 because, again, there's some nuances here, not worth delving into, but you can't run on standard ports without additional infrastructure. So that's it. So 5-ish whatever minutes, we have this this portal up and running. Let me just make it a little bigger. And so this is actually using TerraFusion, the Terra data set from the EOS, and so the data is actually hosted on an endpoint in the open storage network. So it's got some pretty high-speed storage that's sitting out there, and this is the landing page. And there's 3 sets of pages that are available here by default. And of course, this is an open framework, so you can extend it however you need to for your purposes. But this landing page is akin to that other one that we saw on the AC/DC portal that had all the different projects. So think of this as the same, except here that's not as fancy with little boxes. So we just have one project here, this Terra project, and you can see the index looks very similar. It has different facets because this is a different data set. So this has to do with satellite orbits and things like that, and locations and what have you. So I can apply the filters and filter my results down. That wasn't a very good choice of filters. So that's really all there is to it as far as getting it up and running. As I said, we've spent a lot of time trying to get it so that it's packaged, nicely integrated. So you'll see results. You can click on results, and what happens is you get these links that are automatically generated. So you can either go and access the data, just copy the link and just access it as a browser link. You can download the file directly in place here. When you do that, you'll be asked to authenticate, to grant permission again to allow the system to download. Ooh, and that wasn't a good thing. I'm not sure what that was. Oh, maybe there's something wrong with the endpoint. I'll have to talk to them about that. Okay, well, so let's go back here. Or if in the case of, and this is probably more common, when you have large data sets, what will happen is, yeah, it looks like this endpoint is probably down for maintenance or something. Yeah, okay, so there's something wrong with the endpoint. I apologize about that. What's interesting is that you can see the index still, which is, so this is a good illustration of that MRDP, that science DMZ pattern. So you've got the index, and all of this stuff is hosted. So the index is hosted on the Globus service. The portal is running somewhere else, and then the data sitting on an endpoint somewhere also remotely. Once that's up and running again, you've got this nice pipe that to move the data, but these other bits can sit pretty much anywhere else. So that's sort of the plain vanilla portion of it. The big thing here, of course, is search. So I do want to spend a little bit of time talking about the Globus search service, so you can understand a little bit more detail about what's really going on here. So let me just find a decent starting point to walk through a couple more slides. Okay, so let's talk about search. So the one thing that the search service allows you to do is to apply different access policies to the data and the metadata. So you can keep those two things separate. And this is very useful because a lot of times you may have some people that have access to the data, but in order to get there may be metadata that they should not be exposed to. And so you can control access to some of that metadata, and you can do it in a very fine-grained fashion. So a lot of what search, the Globus search service is about, is really controlling in a very detailed manner access to every piece of the metadata repository. And it's particularly useful in situations where you've got CUI or protected data or PHI, where just the metadata might have sensitive information in it, so you don't want to expose that. So you may have that locked down. You may only share de-identified items, and then if the user has access to the data through the other sort of parallel access path, then they will actually get the data after the fact. The other great thing about Globus Search is that we chose a long time ago not to be part of the schema wars and the schema religions, trying to agree on a single schema for everything. I think most people have given up that a while back. But what Globus Search allows you to do is define your own schema, so you can decide what metadata attributes make sense for your application, and you can generate the appropriate metadata from your data and put it into the index, and whatever Globus is given, as my good friend Steve used to say, give us your unwashed metadata masses, and we'll take care of it. So so that's what happens. You ingest the metadata, we create the search index, and then you can query it. And there's two ways to query: simple and complex queries. So the metadata looks like this. It's basically a JSON object. The subject is the thing that is the thing that you're looking for that's being indexed. And sorry, that's the target of the search, and then the metadata, the things that are being indexed. And we have, because a lot of the indexes that you deal with at scale, obviously very large, obviously it's big data, but also big indexes as a result. We have a model where you can do these bulk uploads and creates and updates to the index. So you submit these tasks to the Globus search service that says, here's a ton of metadata, go do something, go create new entries, or go and update entries, or what have you. And once you've done that, the other thing I should point out, this is where that fine-grained access control comes into it. So here I'm saying that for this item in particular, is only available to this iGlobus identity, this individual user, which would obviously be quite rare. That wouldn't be a very helpful thing. But there may be cases where you want only the admin to see that, or you only want the client itself, the actual client application, to see that. So it's limited either to a single user or a group of users typically, or the client. And then when you're querying it, the simple query is just specifying some parameters on the URL. So you can just do get XYZ search index and then a query string. So here I'm getting all HDF files. But the more interesting one is this one here, which is when you want to filter the query along different facets. So you want, all of these things that were, all the readings that were generated between these times on this instrument, etc. So you can do all of that interesting stuff. And this actually does a post. So you give it there's a whole, it's like a query document, like a filter specification that you push out, and you get results. So I'm not going to do the working with Globus search. This I recommend if you are going to experiment or try your hand at building an index. This is actually a very, very good repository that we have. It's all open code. You can look at how it's done. It'll actually create a metadata, an index, a Globus index, Globus search index using on a file system, on a directory. So you point it at a path and it will go and dig down to the path, pull the metadata and push it into the index service. Instead, what I'm going to show you is, if we go back to that portal, how you could, once you have that index, because that, I'm sort of in a sense waving my arms a little bit at the index, because it's as simple as it can be. In most cases, it's actually a very hard thing to do well. And the difficulty stems from being able to get the metadata, to extract the metadata automatically. So we actually have a separate project that's been running for a while that's designed to help automate and do more intelligent things around extraction. But by and large, I'm sure if you've dealt with this before, you've had to write extractors. So the idea here is you figure out how you're going to extract your data. As long as your extractor can push it out in just a basic JSON format where you can add a couple of header fields that we recognize, then you can push it into Globus search. So I'm going to just break the system running here. So I'm going to switch back to my repo here, and I'll talk about the 4 things that we're going to change. So literally, there are 4 files that have to be, actually, technically only 2 files have to be edited, but then it doesn't look great. So I'm going to edit 4 of them so you can actually see real results. But the first file that we have to edit is this settings file for the search index. So that's where you define the actual how the index looks and what facets are exposed and so on. So I'm going to go ahead and edit that. And I have sample code for what the replacement should look like. So I'm going to bring this over here. So this is what it looks like right now. And in the repo, I have a replacement search.py. And we're just gonna update this search indexes block. So you can see here, I'll pull up the portal as well so you can map one-to-one here. So this is where all the metadata are defined here. So files, dates, titles, etc. And then very importantly, here are the facets for searching. You can see them listed here, location, dates, right, all across here. And you can see the different types. So the orbit one is one of the more complex ones. It has a very large range of values. You can't have, 240 whatever. So we have this histogram approach, so you can break it up into chunks and you can specify the size of the chunk and all of that. So really kind of pretty powerful, simple yet powerful. So we're going to basically get rid of all of this and just going to put in something that's a lot simpler. So this this new data set that we're going to point at just has it's a small number of files. It's actually the lady data, the low altitude, the disaster imaging for FEMA. So it's another open data set. I think has some really interesting content. So I'm going to copy this and paste it in here. And now I'll just save that. And what happens, actually, I should probably go and make sure the portal is running in the meantime. So let me go and run that in the TMAX session quickly. Sorry, just give me a sec here. Oops. Okay. Too many commands. Okay, I'm just going to run it here and have it running so that as I make changes here, you can see them materialize on the screen. So that's running there. Where's my portal? So here's the portal. It looks good, but if I refresh now, it should look quite different. Okay, so now I'm pulling data from this other search index, just like that. Here are the new facets, and here's the new data set counts. It's a much smaller data set, obviously. Here are some of the files, but notice these things are now broken because the metadata I'm getting is different. This data set is all about images and geopositioning and altitudes and things like that. So it has nothing to do with satellite and instrument orbits. So what I have to do is go and change one other file to get the right data. And that file is the fields file. The fields file defines, as the name suggests, the fields that are used in the index, and it transforms them as needed. So the current fields file, which is also in here, in here. So that's the fields file. We're going to edit that. So this is what it looks like right now, or what it looked like for that the Terra data set. You can see where the transformations are made. So this is the endpoint, the HTTP, the DNS name for the endpoint where that data lives. We have a different one. And then this is the Globus endpoint if you want to go and do a bulk transfer. So we're going to do the equivalent here, except we're going to use different endpoints and, most importantly, the different metadata. So we have a totally different, mostly different set of fields. We still have, most data sets have things that are, like a title and a date or some kind of publication or whatever date, contributors, things like that, data site type metadata. But this one, this is what it has. So like I said, it's got latitude, longitude, etc. I'm going to save that. And if I go back to the this page here, we should now see, we don't see it yet because I don't have it in the template. So I'm actually seeing the actual data is actually there. And I can click on details and you can see it's picking up some of the data here automatically because that's the standard format. We don't have general data site type attributes in here, so that's blank. But we don't want that. Obviously, that's kind of ugly. So I'm going to make two quick changes. One is so that's sort of on the structural side. So essentially now you're basically done. You're getting data from another index, and you can click and go and do the exact same thing. You can click on here, and you can go into Globus and look at the data and move it, etc. So that's all just there. I'm literally editing a couple files. the thing you would probably want to do, I'm sure, is actually make it look nice and sort of usable. So at least for this example, I've got a couple of replacement templates. So there's this one, which is that detail page, so we can fix the metadata on there. So I'm going to go and edit that. So that's in where are we? Oops. It's in templates, Globus portal v2. Yeah, so this is the file here, the detail overview. Okay, so this is what is shown there. You can see this is the general metadata on the side. This is the block for the data site metadata. We're just going to get rid of all of that because we don't have data site metadata here. We just have straight up whatever those fields were. So I'm just going to copy paste the whole thing and save it. And now when I go back here, you'll see this has changed. And now I'm just seeing the metadata that I have. Pretty straightforward. And then the last little thing I'm going to do is go back here and change the index results page. And that is in here. So this is search results. So we're going to go, let's see, to components and search results. Again, this is where those fields were showing up with the metadata, the location, etc. Right? So those 4 fields. We obviously want different ones. So I'm going to just copy all of this. This is actually a much slightly simpler, shorter template. So all we're going to show on that page is latitude, longitude, and altitude. And when I do that, voila, we're done. So we now have, and again, 5-ish minutes, okay, because I know my way around. Maybe first time out might take you 10 or 15, but pretty quick once you have that index created, which again, I don't want to sort of trivialize the magnitude of that effort. It can be quite substantial, but you have an index, and this is, I think, a great way, one good way to consume it. And some of the things that we have built or done with folks or helped them build is like integrating compute capabilities into this. So for instance, here, let's say, so like this, I think these are all images. So I could actually just click on one of these and download it. And you can see I was doing this one earlier. It must be a popular one. So, you know, this is, again, this is disaster area photos, some unfortunate scenes. But point is, you know, especially in large imagery-based data sets, you don't want to be like downloading and, oh, that's not the one, right? So you want to maybe want something like little thumbnails or something, or previews. So one of the things that we have, another site, is you can go click a button, go create a preview, or you could do some additional analysis, what have you. Or you can, instead of having all these individual ones, what you can do, say, okay, I've narrowed down my selection. I want those 27 data sets from that survey in that year. Go get them all. So there's like a button here. It's, think of it conceptually like not quite a shopping cart, but it's like, you know, because these data, the actual data of the files themselves may be spread all over. Remember, all we're looking at here is an index. We're not like browsing a storage system or anything. So you know, where we go to get it, in this case, it just so happens that everything is on one Globus endpoint, and I can get to it, you know, via whatever, HTTPS. But in many cases, it's spread. And so the ability to say, get me all these related data sets with one click, that's a huge deal. And it will fire off the transfer, and will pull the files from wherever and put them all in whatever location you specify. So that's a very, very powerful integration. Yeah, so that I've thrown a lot at you there. We've got about 15 minutes. I could talk more, but I'm sure everybody's kind of zoomed out by now. So I'm actually going to stop there and open it up to questions and see what else people are interested in, what else I can answer for you. And I'm happy to poke around here more if you want to look at other things too.
Yeah, hi Vas. And there are two questions from Aparna. Will the slide deck be available to the attendees? Is there a recommended way to post offline questions, contact email, or GitHub issues? This is cool.
Yeah, so by all means, so you can email me directly, vas@uchicago or vas@globus or vasv@anl.gov. lots of ways, but vas@uchicago works mostly. If you're working on something already and you run into an issue, by far the best way is to just email support@globus.org. That gets triage between a help desk and the engineering team. And I look at a lot of those tickets as well. So that's, I'm mostly responsible for customer and users and that. So yeah, and if you're really are looking at building or extending portals or things like that, or doing any of the automation stuff that I talked about earlier, in particular the automation flows, we're very willing to help you with that. We're happy to make substantial time investments, especially on flows, since it's an early service. So we're looking for people to put it through its paces. So if you have interesting use cases where you think that level of automation might be suitable, by all means, please reach out. I'd be happy to have a conversation, even if we don't end up being able to help you or working with you. I think it's very informative for me to be aware, and maybe we can you can get something useful out of it.
A few more questions from Aparna as well.
Sure.
If the data gets updated periodically, or if the collection grows, does the portal reflect that instantly or require additional configuration setup?
If the index schema doesn't change, in other words, if you don't add metadata to future entries, then everything will be reflected. And so as soon as it's in the index, it will be, there might be a small delay while the index gets synced and replicated, but yeah, it will show up immediately. If you decided, you want to add, I don't know, whatever else to here, device and whatever, humidity, and then you would have to, you would firstly have to change the definition here in the fields, because there will be additional fields that you want to get out of there. And if it was something that you wanted people to search on, you'd have to change the facets. But again, it's literally a couple of configuration tweaks. So this is not, it's code, but it's not, it's sort of more like configuration settings. And then again, it's reflected automatically. And you can also, I should mention, you can also update the index, so you can do bulk updates as well, and those will be reflected as well.
And one more question. The data endpoints can also be AWS S3?
Yes, absolutely. And in fact, up until the other night, I had all this, the lady data is actually, in fact, I still have it on here. I have an S3. So this is actually the S3 data, the open data, they host a bunch of the open data sets, and I have endpoints available to access those. Yeah, so you could have it S3, you could have it on Google Cloud Storage. Google also has some open data sets that we use from time to time for these tutorials. Yeah, absolutely.
I have one simple question.
Yeah.
Does it require Globus 5?
Does it require, sorry?
The Globus version 5 currently?
most of these connectors do require Globus Connect Server version 5. Yes. We're rapidly moving away from 4. We will support it for quite an extended period still, because a lot of places, including NCAR and others in Boulder, have version 4 endpoints. But we've been rolling out migration tools for the last 2 or 3 months in cohorts. So eventually, probably in the next 4 to 6 months, I think we'll be at a point where everybody can migrate automatically, because yes, for all of these connectors, you do need version 5.
Thank you. Any more questions? Perhaps you can unmute yourself and ask if you want.
Yeah, stop sharing and. No. Yeah, thank you very much, everybody, for giving me the opportunity. Thank you to the organizers. I will get these slides made available. I know I had that link that was sent, but as always, I'm working up until the last minute, so I will get those posted shortly.
And this being tutorial, you can hang on for next 10 minutes or so that people can ask questions with more.
Yeah, absolutely. I'm here. I'm available, and actually, if you did want to follow along but just didn't feel like it after a long day, I will have these instances up and running for another couple of days. So you're welcome. You can save that link, that spreadsheet, and go pick an instance and run through some of the stuff once the slides are posted.
Thank you, guys.
Sure.
Kyle, are you ready to start a little early?
Yeah, sure. Happy to start early.
Why don't you go ahead and share your screen?
Sure, sounds good. Start video. Okay. Can you see my presentation all right?
Yep, looks good. Thanks.
Okay, great. Okay, hi everybody, thanks for, sorry.
Sorry, Kyle, let's try to maintain that time, because if someone is targeting for your particular presentation, they may miss a slide or two. So
yeah, sure.
Yeah, let's be respectful.
Okay, so we can wait. No worries.
And thank you, Vas, for your nice tutorial, and I hope it will be helpful for the participants.
I hope so too. Thank you very much for the opportunity.
Okay, we are right at 3:40. This is last talk of today's session. So today, Mr. Kyle and Dr. Nachiketa will be giving a presentation about XCast, a high-performance data science toolkit for the climate forecasting. Mr. Kyle Hall is a staff associate on the International Research Institute for Climate and Society's data library team. And Dr. Nachiketa Acharya is a research scientist at the Cooperative Institute for Research in Environmental Sciences series at NOAA. So thank you, Kyle and Nachiketa. Please go ahead with your presentation.
Hi, thank you so much for that introduction. Can you hear me okay?
Yeah.
Okay, perfect. Yeah, hi everybody, I'm Kyle. I'm here to present XCast, which is a long-running passion project of mine and Nachiketa's. We've been developing this for the past year in pursuit of better climate forecasting. And so I guess I'll get right into it. To start, I just want to give some background on general Earth science data methods. As a lot of you are probably familiar, Earth scientists use high dimensional gridded data, meaning data that follows grids of latitude, longitude, maybe altitude, pressure, other things like that. And there's obviously a lot of insight to be gained from all that data. So there are a couple of ways to approach statistical and machine learning based analysis with gridded data. You can reduce the dimensionality with aggregation across dimensions, like taking the mean sea surface temperature, for example, or you can use a pattern regression approach, like principal components regression, to mathematically derive some sort of index of a pattern in a climate phenomenon. Or you can just go ahead and apply the same statistical or machine learning approach at each grid point independently. And that's kind of the thing I'm going to be focusing on in XCast. So grid point wise operations, just to be clear again, are operations applied independently at each grid point. They're useful in certain cases. I'm aware that there's somewhat of a discussion surrounding the appropriateness of the application and various things, but in certain cases, it's definitely applicable. And so just to be clear, what it's not doing is training a single, say, neural network at data from multiple points in space, and it's not taking into account the spatial relationship between points. So the statistical relationship for your model trained in New York, we won't know anything about what's going on over in California or something like that. So yes, there's a lot of tools in Python. To be clear, everything that I'm talking about today is Python based. A lot of tools in Python for manipulating gridded data. A lot of people are very familiar with X-Array. It's an extremely powerful n-dimensional labeled data manipulation tool. And there are also a lot of Python data science utilities. Maybe most popular one being scikit-learn, implements a lot of traditional statistical analysis tools and things like that. The problems start to come when you try and mesh the two of them. So Python's data utilities are generally incompatible with its gridded data libraries. There are a couple that attempt to bridge this gap, and they do so with two pretty good effects, like Klimpred and METPI. Both of those, as the names kind of imply, are a little bit domain specific. So Klimpred works with model verification and ensembling. METPI does meteorological things. And so that kind of gets into why we decided to build XCast. We wanted to build a tool that would bridge the gap between Python data science utilities, which work in 2 dimensions, and n-dimensional gridded data utilities like X-Ray. We wanted to not just build a tool that would work for one case. We wanted to do something that would more generally be applicable to gridded data. In fact, the only requirement of XCast is that your data be 4-dimensional. And this is pretty well in line with the standard use case specifically for climate forecasting. We've been focusing on multi-model ensemble forecasting. And so generally the dimensions we work with are latitude, longitude, time steps like years, and a set of ensemble members. We wanted it to be easy to use because I mean, in my opinion, there's no reason that it should take hours upon hours of coding to apply grid point-wise operations to some earth science data. It raises a significant barrier to earth sciences, in my opinion, yeah. And we wanted it to be high performance because grid point-wise operations, in the words of Dask and X-ray, are embarrassingly parallel. There's no reason why we shouldn't be leveraging all the compute resources we have. And so XCast, as you can see, gets its name from X-ray and forecasts. While forecasting isn't the only thing that XCast can do, that was a good option for us. You can see XCast comes with all the everything you need to do statistical bias correction or machine learning based multi-model ensemble forecasting, any number of statistical methods. Anything from data pre-processing like decomposition, regridding, rescaling, etc., model training, k-fold cross-validation, computing skill, and all that. There are also some visualization utilities, but those are still under development. And so just as an example of what XCast is meant to do, I've set up some work that Nachiketa and I have been working on here, doing seasonal forecasting of Indian summer monsoon rainfall. Here we use an extreme learning-based multi-model ensemble approach. Extreme learning machine is a neural network-based nonlinear regression method. It's appropriate for grid point-wise operations because it's extremely fast compared to a normal neural network trained through backpropagation. Extreme learning machine is basically has its hidden layers frozen and then its output layers fit with a more Penrose generalized inverse. In this case study, we used North American multi-model ensemble data and as the predictor, and India Meteorological Department rainfall data aggregated over the June through September season as a predictand. Here you can kind of see the spatial distribution of rainfall during that period over India. So this is an example of where one might start, for example, in a climate forecasting workflow as a Taylor diagram. It's generally used for examining the relative skill and not necessarily skill specifically, but how the ensemble members capture various aspects of the observation data. And this is produced with XCast. So here you can see skill maps and receiver operating characteristics curve, both produced with XCast again. Generally, the workflow involves pre-processing the data, training models under cross-validation. In this case, I believe we used leave 1 year out, cross-validation. Making predictions, calculating skill, and then post-processing. So this map you see here actually has 3x3 Gaussian kernel smoothing applied. The grid point-wise approach can sometimes appear random, but you can also, because like everything's so independent at each grid point, but that's one way to address that. So we have also used XCast in the ECMWF S2S AI challenge. This was a challenge put out by ECMWF and the WMO to improve the prediction of subseasonal to seasonal timescale precipitation and temperature. So we used XCast to implement something called the probabilistic output extreme learning machine, which is a modified version of extreme learning machine that Nachiketa and I have been working on this past year. And this map that you can see here is actually, I'm sorry, I apologize, it's kind of small, but it represents the rank probability skill score of the POELM method when compared to the like state-of-the-art bias corrected ECMWF model. In this, we actually did a 3-model multi-model ensemble. And these are at lead time, or sorry, the week 3, 4 and week 5, 6 target periods. Yeah, so just to illustrate what XCast does. So let's kind of get into how XCast works and what it, like what's going on under the hood. Just for background, for background, we're going to be talking a lot about chunks, and I don't want that to sound like complete nonsense to everybody. I'm sure that some of you are aware of it, aware of the terminology, but just thought I would go over it again. So in XCast, the way we treat gridded data is that rather than treating it as one giant matrix, we can actually split it up into smaller matrices in the spatial dimensions. Since all the operations are independent spatially, they allow for this kind of spatial chunking. And so when I say a chunk, I mean, I'm going to be referring to a group of grid points which are close together spatially. Yeah, and so this chunk-wise parallelism allows you to split up the job, basically like doing one location on one processor while you do another location on another processor. So that has a great opportunity to improve performance here. And so once we had implemented XCast using this chunk-wise parallelism, I wanted to compare it to like the other the other possible ways of doing this job. So the grid point-wise operations, like the first instinct would be to use for loops if you're not like a high performance computing person. And so you included that here as a benchmark. As you can see, based on this graph on the right, for loops are kind of a clear lose compared to other options. And that makes sense, right? Because there's no parallelism there. Another interesting observation you can make from this graph on the right, which by the way represents computation time as the intensity of a compute job increases. And here the analog that I'm using for job intensity is the number of fits at each grid point. And that makes sense in the climate forecasting world because in methods like ELM, extreme learning machine, and POELM, and those actually stochastic in nature. They're randomly initialized, so you have to run an ensemble of say 30 plus models in order to get a more meaningful result. Yeah, so the other conclusion you can draw from this graph on the right is that Xarray apply ufunc. So Xarray is a powerful gridded data utility, and it has an out-of-the-box function called apply ufunc, which allows you to apply an arbitrary function across some certain set of core dimensions. Yeah, the notable point being that Xarray apply ufunc compared to XCast with only a single chunk as in no parallelism, the data, like your data set is completely contiguous. They perform almost exactly the same, and that makes a lot of sense because under the hood, they both use Dask, which is an extremely powerful Python high performance computing and multiprocessing library. They use different Dask functions though. And so the other conclusions you can draw, like when you increase the number of chunks with XCast, there's some overhead introduced, the rechunking and dispatching of the different jobs to different things, and introduces some overhead. And then since XCast uses Dask, you can also spin up a Dask distributed cluster of various sorts. The cluster can be like an institutional compute cluster, or it can also just be what they call a local cluster, which means leveraging multiprocessing on your local machine. And that's actually what I've done here. All these experiments were performed on my 2015 MacBook Pro. So not exactly a high performance machine, but you can see that once you get into multiple chunks and multiple cores running on a cluster, that's when the parallelism really starts to shine and you get a big performance win. Yeah, moving on. This is just another analysis of XCast performance using a different analog of job intensity. So rather than the number of fits at each grid point, I used the number of samples at each grid point. In the seasonal climate forecasting context, there's very few samples. Apologize. Yeah, in the Indian summer monsoon rainfall example I showed previously, there are actually only 37 years of data. So on the left side of this graph might represent more closely seasonal forecasting situation, while the right side might represent like a S2S or sub-seasonal forecasting. And either way, you can see that that XCast using a cluster of 4 cores and multiple chunks is a clear performance winner in this case. And so one question that might be asked is, well, I said X-ray, apply ufunc, and Dask or XCast both use Dask. They use different functions though, but like really, what's the difference? Like, why can't X-ray, apply ufunc benefit from this Dask parallelism as well? And that's a question I don't really know the answer to. X-ray, apply ufunc is designed to be very general. Like you can use it in like pretty much an arbitrary situation, computing over arbitrary sets of core dimensions, and yeah, it's rather it's a broad function, whereas XCast is doing a very specific job in the best way that we could basically. The constraint of only having 4 dimensions and then only applying it over this parallelism over the 2 spatial dimensions allowed us to really put a lot of time into getting the best possible performance in that situation. But yeah, there needs to be more research done about that. And so this kind of begs the question, like, okay, well, we know that our best performance comes when using multiple chunks with XCast, and our best performance comes when using multiple processes. But how many of each should we use? Well, obviously, the ideal situation is you process each grid point on a separate computer, but that's clearly not possible. So I did a little bit of analysis here. And the main takeaway from this graph on the right, computation time versus chunks, number of chunks for these are the MLRs, multiple linear regression, and ELMs, extreme learning machines. So two different like statistical machine learning methods and 2 different size clusters basically. And I think the lesson from there is that once you get the number of chunks above the number of cores, your parallelism has become worth it in this case, because when you only have 1 chunk, but you have 4 cores, 1 core is going to do that chunk and the other 3 are going to sit there doing nothing. But if you have four chunks and 2 cores, then they can each do 2. So you actually get parallelism there. And so, yeah, you can actually also, this is on the bottom left here, just an example of an XCast workflow using a Dask client. You can point that client, this is like kind of a made up IP address, but you can point that to like the scheduler of any institutional cluster. It's Dask compatible. Or you can pass an n workers argument to control the level of local parallelism. And then, yeah, so the other constraint with XCast is that your predictors and predictands have to be the same size spatially, so be on the same grids. That's why we built a regrid function, and they have to have the same chunks along the spatial dimension as well. So that's what the align chunks function is there. And so you can see, if you're familiar with scikit-learn, that this kind of API we have here closely mirrors that of scikit-learn, fit, predict, proba, transform. It's designed to be easy to transfer knowledge of scikit-learn to XCast and apply your knowledge of Python data science utilities to gridded netcdf data. Yeah, so this slide shows a sample of what you get. Another win from using Dask. You get a fancy GUI status monitor. This screenshot of this task stream up here actually kind of shows the increasing amount of parallelism with the number of cores available in XCast. This is a recording of when I ran the performance experiments that I demonstrated or showed you before. Yeah, so I just want to reiterate also, I spent a lot of time talking about XCast performance, but it's actually not purely meant to be a high performance tool. That's not secondary, but one of our other main goals, just as important, is to remove the burden of data wrangling, make it easy to apply these machine learning based and AI based statistical methods to gridded earth science data. Yeah, to lower that barrier to entry that I talked about, of having to implement your own for loops and keep track of dimension names and things like that. There's obviously, the work is never done. We have a lot more thorough testing to do, more analysis of the performance, improving visualization functionality, many other things. But yeah, thank you so much for your time. I'm gonna close out here and open the floor to questions. So I really appreciate you tuning in. Thank you.
Thank you, Kyle. If you have any questions, please go ahead and post it in the chat, I mean the Slido, or unmute yourself and ask. We have a little bit of time. If there are ones, it looks like it's a little tiring for the last talk of the day.
Of course.
So let me thank you, Kyle and Nachiketa, for this exciting work. And thank you for participating in this workshop to present your work.
Oh yeah, I'm sorry. One more point. Nachiketa would normally be co-presenting with me, but he's not feeling well today.
Yeah, that's what he told.
Yeah, thank you again.
Bye.